The homework, problem number 2 and 3, they can be solved just by that MATLAB 5, right? So the whole idea behind this guy was to be able to learn how to use XTeam, how to actually get H or X or S or T or whatever, right? It's basically that statement, huh? Just to say that H1 is XTeam of H and P, H underscore P and T. That means I want the enthalpy and I'm going to give you pressure and temperature. And what value do I use? P1 and T1. What's P1? 6 bar. And what's T1? 200 degrees C. Is bar and degree C what we should use in our calculation? No, we should use Kelvin and Pascal. Why we are using bar and degree C? Because that's what the people in the MATLAB, sorry, in the XTeam code wrote. So we have to follow their ingredients. If we want to make their cake, we have to follow the ingredients, right? So the same thing for a lot of engineering handbook. Like they will have like weird units, and but you don't have a choice. If you want to use the formula or the table, the design table or whatever, you just have to follow the recipe, right? So that's why you can see here in this line, huh? How I am struggling to stay SI, because I know the H need be in joule per kilogram. Any calculation, H in joule per kilogram, not kilojoule per kilogram, right? Because if you want to add the V to this calculation, V is in meter per second. So you have to make the enthalpy in joule per kilogram, right? But the H that I just got, H1 that I just got from XTeam is in kilojoule per kilogram according to their handout, according to the recipe. So that's why you see H1 times 1,000. Now I am kosher. Now I'm using joule per kilogram plus V1 square over 2 minus V2 square over 2, right? Correct? And then just before the end, now I'm going to get H2. It's going to be in joule per kilogram because everything should be in joule per kilogram. Just before the end, I divide over 1,000. Why? Because that H2 is going to be used later on to get what he wants, right? So I keep my calculation SI, and just before I give it to the customer, you want the stuff in, BTU per pound mass, I just have to convert to those units. And that's actually the homework this week. In the homework this week, we'll see a power plan when you want to calculate stuff. And I'm asking you to calculate things in BTU per pound mass. And I think I did say last week, and if I didn't say, let me say it again, never use pound mass in your calculation. It's not right unit to use. For mass, if we want to stick to English unit, we don't use pound mass, we use, can hear, slugs. We use slugs. But at the end of the calculation, he wanted in BTU per pound mass, fine. I just convert in the last step. Okay? So that's my advice. All right? So you want to see if there's anything in the chat? Yep, okay. So let me actually see this. It's annoying to me. Okay, so I just want to say that, as I said, I mean, we saw this before, but let me just say that I really appreciated when people start from here, when they start from M, E, control volume, plus m dot out. And then over here, they will put the h plus the v square over 2 plus gz minus m dot n h plus v square over 2 plus gz. And this is out, and this is in. There is something nice about knowing what is the general equation, right? So of course, you can cancel all this thing because it's a convergent divergent nozzle, and it's isentropic, and there is no work, and you eventually end up going like this, right? As we said last time. And you shouldn't lose points if you just did this, but again, there is something really educational about starting at that line. All right. Everything here should be in SI. That's why this was in meter per second, and that's why this is joule per kilogram. Okay. So in that code, you saw that like I was calculating the entropy. It's not required. All he wanted was the temperature or the X. Well, on the TS diagram, usually the inlet of the turbine is here, and then you expand from that pressure, say 6 megapascal, actually it was 0.6 megapascal. Why it's flickering like this? The light. And this is 1.3 megapascal. And so if you go isentropically downward, you will end up like this. Okay. And if you are not isentropic, you go to the right or to the left. If you have an adiabatic but not isentropic process. What's isentropic? Not just adiabatic. We said last time adiabatic and reversible. No losses. So that's how you go up like this. If this is 1, this will be 2s. But if your process is adiabatic but not reversible, entropy can increase. And if the entropy increase, we go to the right. On the x-axis, we go to the right. So state 2 need to go to the right, need to be here. So that's why he was saying that if you are superheated, get me the temperature. And if you are wet, if you are inside the dome, give me the X. So T2 and X2. So why if you are wet, you didn't ask for the temperature? Because the temperature is already set. If you are 0.13 megapascal, the temperature in the steam table will tell you 0.13 will correspond to megapascal, will correspond to what? 107 degrees C. So you don't even need to do the first law of thermodynamics on the equation, right? But you could end up at different X depending on the thing. So in the code, I was trying to see if I was isentropic or not, right? By calculating the S1 and S2, but you don't have to do it, right? But it would be interesting. Of course, in order to run, he will give me an error now because I didn't, well, I did run Xteam, I guess, or I didn't. Let me run Xteam first. So he need to run Xteam so that he know where it is, right? And then after that, you would run your homework 1 problem 4. And he did run. And so the temperature is 107 and the X is 0.99. So that's like slightly inside the dome, right? And interesting, if you look at the entropy, 6.9 and 7.2. So it did increase a little bit. You went a little bit to the right. Okay. So that is a big deal, the entropy, to be able to tell that there is an increase in entropy, then you can tell whether the system is behaving correctly or not. Or think when I was undergrad, there was this problem when they give us an engine and they say, well, an engineer claimed that he invented that engine that made that power and make this energy, and validate his claim. And you do this by calculating the entropy. And if the entropy actually didn't increase, sorry, yeah, if the entropy didn't increase, then that is basically totally not true, right? It cannot be working like this. But let me, since we are talking about this, and we're going to talk about cycles today, right? Let me ask you, is there any way the entropy will decrease? On that TS diagram, am I saying that the only way is always going to the right? Like everything should go to the right, we never go to the left? Because if we're going to make a cycle, and we will make Rankine cycle today, a cycle means that you go back to the starting point. You start from a place and you go to at the end of the cycle, you just go repeating yourself. So what will make the entropy go the other way? Because I want to go the other way. I want to go where I started. What will make what make the entropy increase? What make the entropy increase? Irreversibility, losses, mixing, all the bad stuff, huh? What does make the entropy decrease? Anyone? Can't hear you. What makes the entropy decrease? No. What else makes the entropy decrease? Anyone online? What makes the entropy decrease? It does. I mean, I need to go back, right? A cycle need to go around, yes. Decrease available energy? No, but you are close. It's what? I mean, what is decreasing the available energy? I mean, something similar to this. If we remember, what is the second law of thermodynamics? The first law is what we wrote right now. Q minus W, conservation of energy. The second law, they usually give you a statement for it. They will tell you there is no heat engine that can take heat and generate warmth without rejecting heat. That's the first statement of the second law. Another way to say the second law is to say there is no heat transfer between cold and hot. Of course, the heat has to go from hot to cold. But if you want to make the heat go from cold to hot, if you want to take heat from this room that's already cold and send the heat out to the very hot ambient outside. How hot was it right now? 90? I read in the morning it was like 100 degrees C. You guys, I have been here since the morning. I have no idea how hot it is right now. Really hot, right? So to take heat from the cold room to the hot environment, the second law will tell you cannot do this without work, without mechanical work. That's the other way to say second law. But there is, after those two statements, there is actually an equation that say here is the second law. And that equation is delta S, the change in the entropy, greater than or equal delta Q over T. That is the second law of thermodynamics. And this delta S is the change in the entropy. And D, it's like, like how they say DT and DP, that's the change in the property. But when it comes to the Q, they make this weird delta. Why? Why they didn't say DQ? Some book write DQ, but that's wrong. You have to write this weird delta. I can't hear. It's not exact, no. That symbol mean no, that symbol mean this is not property. Q is not a property. Pressure and temperature is a property. Q is not a property. I mean, you're standing the air in this room, you can say what's his pressure, what's his temperature. But you cannot say what's his Q. What do you mean what's his Q? Right? So anyway, this is the second law of thermodynamics. So based on this, what will make this guy negative? So for the entropy to decrease, delta S need to be negative. What will make delta S negative? Excellent. So that tells you the only way for the entropy to decrease is cooling. So for delta Q to be negative, if I have a jet engine or a classroom building or this is negative Q. And this is positive Q. So to make negative Q, you have to get heat out of the classroom, heat out of the, right? So then on those cycles, the steam power plant and the jet engine, like gas turbine power plant, to make a cycle, you'll always find cooling tower, cooling exchanger. There should always be something that take the heat, right? And so that the entropy go back again. And that's why the second law statement is saying you cannot have a cycle where you put work, you put heat, and you take work without heat rejection. You have to have heat rejection so that you can go back again. Okay, and so when I look to a jet engine or a steam power plant or any control volume, and you are telling me you have to give Q added over here, and you'll get some work, but you always have to reject heat, right? Otherwise, it's not, you will not be able to go into a cycle. First law, not second law, first law will look at this box and say what? What does the first law will say about this? That Q minus W m dot delta H, the conservation of energy. When you look to that cartoon and you want to apply the first law, what would you say about this? What does the first law say here? You will say Q added equal work plus Q dot rejected, right? Input equal output. This guy coming in, he split some work and some Q rejected. And the second law say this is very important. This term, you cannot get out of that term. So that lecture today is called isentropic efficiency and American cycle. So the efficiency of a plant, of a heat engine, anything that take heat so that he can make work is, what is the efficiency by definition? It's the net work net, divided by Q added. This is what you get, and this is what you pay. I mean, this Q added coming from what? Burning natural gas, consuming nuclear fuel rod, right? I mean, someone need to generate that heat. So because that guy is always going to be smaller than this guy, why W dot is always smaller than Q added? Why? Because this exists. This has this cut. It's like in casino. This is a house. The house always need to win. So you have to pay, someone need to pay Q rejected. So that's why this eta will always be smaller than eta 1. As a matter of fact, coming from the second law, it will be always smaller than eta kernel. Okay. I was reading the ASHRAE magazine this morning that was issued this month. ASHRAE is the American Society for Refrigeration, Air Conditioning, and Ventilation Engineers, right? And they had one article about Carnot, and he actually, I didn't know that he died at 36 in cholera pandemic. The guy, obviously, I mean, 36, and he already made a name for himself. So that was amazing. So what is eta Carnot? That is the ideal cycle. Okay, so all the cycles in our power plants, we all just try to be similar to this one. Why it's ideal cycle? Because I mean, you cannot make a machine like it. it looked like this on a TS diagram. Okay, so this is constant temperature heat addition. Constant temperature heat addition. You are adding heat and the fluid is not getting hotter. Okay, and then is that possible or impossible? Actually, we will see today this part. You think it's impossible, but it is possible a little. And then this guy, what is that? Isentropic expansion. You need a turbine that takes you from this to this isentropically. A turbine that has no friction. The steam will go into the turbine plates without basically sliding on the wall, without having any friction. Is that possible? No, it's not, right? So the actual one will have to go to the right or to the left. The expansion will have to go to right because the entry will need to increase. If you give me friction, the entry will increase. And then come the heat rejection, right? And that will take me here. And then again, isentropic compression. So I need a pump or a compressor that go up without a single joule of friction on the wall. So if you do this, if you have this cycle, and we will see how the cycle, Rankine cycle, how does it look like, and why do they try to get closer to this rectangle? So a Carnot cycle will look like a rectangle in the TS diagram. And the efficiency of any cycle, not just Carnot, is always work net over Q added, right? And by the way, I can make it like this, W dot over Q dot. And what's the unit? Joule per second, joule per second. But then there is that work net is M dot multiplied by small W net. That's the specific work unit, joule per kilogram, and the M dot kilogram per second divided by M dot small Q added. That's specific heat addition unit, joule per kilogram, M dot kilogram per second. So I still get my joule per second, kilogram per second times joule per kilogram, I still get my joule per second. But the point that you cancel those guys. And so then eta become the specific work over the specific heat addition. And so what's nice about this is that it doesn't ask for M dot. Okay, it doesn't ask you for the M dot. But I mean, sometimes we want to ask about the M dot, how much does it take? And today, actually, we're going to discuss your first project, which is worth 5% of your course grade. You said you're going to have total 6 design projects, and today is going to be your first. And so I just wanted, it's going to be easy, but I just want you to get familiar with what is the format of a design project from this school point of view. How do they want you to write make your design project? So in that design project, it's about a power plant that we try to optimize it, and he will ask you to calculate the M dot and the eta thermal. I mean, so you can calculate thermal efficiency like this, and then he specifically said he wants. So we need to remember this equation, calculate thermal, and he asked you for calculating how much M dot is needed in that cycle. To do what? The requirement is, I think it was like 512 megawatt power plant. So that W dot is M dot multiplied by work net. And so if you want this to be 512 megawatt, again, we don't use mega, we use watt, so 10 to the power 6. And he's asking about this, the M dot. So we get this, then we'll be able to calculate the M dot. So those are the 2 important equations. Make sense? Okay. So back again to that. So any cycle, Rankine, Brayton, any cycle, efficiency is work net over Q added. So now for Carnot cycle, that rectangle cycle, What is equation for it? Does anyone remember from Thermo 1? What is the efficiency of Carnot cycle? So that W over Q translate into TH minus TL over TH. Okay, that why? Because it turned out that you actually, if you want to see QL or the Q rejected, it's basically this guy. And if you want to see QH, the heat addition, it's this guy. So basically, this is TH multiplied by delta S, and those guys is delta S. And it's the same delta S. Right? The same width. That is the delta S. So this cancel with this one. And so the eta Carnot is 1 minus TL over TH. And that gives you an upper boundary to what is the maximum efficiency that's available for you. Okay, so if you have hot gases coming from a boiler, from a furnace, let's say at 1000 degrees, again, it's specifically in this equation, you cannot use degree C. Okay, you have to use Kelvin. Kelvin. So if the temperature is 1000 degrees C, so 1000 plus 273, right? And you know that TL, what's TL? The coldest temperature in the cycle. How cold the cycle can get. Like if I have a steam power plant cooled by the air in Tulsa, Oklahoma, probably we cannot get cooler than the air that's cooling us, right? So that TL will be the temperature of the air, right? So in a day like this, it's like 40 degrees C or something. So it will be 40 plus 273. So that immediately tell you what is the maximum efficiency that power plant can work at. So anyone claiming that he has a power plant that runs higher than this, he is crazy, right? I mean, it cannot work. Okay. So having said that, there are things that are not heat engine. So your car running on gasoline, that's a heat engine. Take heat and you reject heat and you make work. That's a car engine and you cannot get higher than this efficient. But fuel cell, car that run in fuel cell, there are some, like Honda makes some, right? They are not that widespread, but if you're running a fuel cell, it's not a heat engine. And so the efficiency of fuel cell can be higher than Carnot cycle. But diesel engine, gas engine, gasoline engine, gas turbine, steam power plant, they cannot exceed the Carnot cycle. Right? Make sense? Very good. So that gives us a good introduction to so first, any question about the homework before I go to today's class? Everything was clear, right? So the answer is 107, right? And the X was 0.9. Yes. That's an excellent point. Excellent question. Yes. So in MATLAB, the Boorman way to actually get this is to do a screenshot of the code and the output, right? But there is actually more fancy way, and that is, you see this tab called publish, right? So you can just do this, and what he does is that he runs the code and he makes the output when they are calculated. Okay, that's not just the only good feature, but also when, like sometime if you need write good code, and that's really good advice for the rest of your career, always add comment yourself. Okay, so because I mean later you would need those comments when you are discussing this with your boss or with customer. I don't remember what unit was it, what I was doing here, and beside the comments that explain say unit or like for example maybe over here I want to write that this is applying first law basically. I want to just tell myself that this was the first law of thermal, right? But what also is nice is that you can divide the code into parts. By doing this, you could say reading inputs. Okay, actually, where is Aldo? Aldo's not here, right? I saw his homework. I was like discussing with Bebin how to grade the homework. And so I found Aldo homework, we're using it as an example. I started reading. He made it beautifully by, in his code, he put his name. So he used those commands to basically say homework 1, 3, 5, 2, 4, and student name. Not only this, but he also did given, right? And he started writing what's given. And I mean, he put the number given, and then he said after that, after what's given, you know, he wrote required, and he wrote what is required, right? And then he wrote the solution. But why this is nice? Because even if the homework does not require you to use MATLAB, and the homework this week, so this week you have a homework, but the project I'm going to assign, but it's not due today. Sorry, it's not due next week. It's due in the on 9/26. So you have like some time for it. So the homework today does not require you to use MATLAB. You just said calculate stuff for me. But I would recommend, even if the problem didn't say use MATLAB, don't use pencil and paper. Actually, do it in MATLAB. Why? One, Steam table is there already in XSteam. Two, when you do things with paper and you want to revise again, there is no room, right? I mean, you cannot try after you spend like 30 minutes or 1 hour typing, you're not gonna write again. But when you have it in the code and you saw something wrong, you can immediately go and change it, right? So it really pays a lot, even if you are not comfortable. One, you have to get comfortable. You need to be able by the end of this course, write in your resume, I know how to use MATLAB. So any discomfort that you have right now, you just have to bite the bullet and get over it and learn. And I am here, Bebin is here, Saqib, by email, you can ask for help, and we are here to get you over that hurdle. And again, we are not asking you to do like big data processing or like, let's plot, I mean, we're gonna plot like in few homeworks, but I just want you to learn a few things. So those few things, you can learn it on your own, or you can reach out and you can ask us for. Yes, question. So you are saying like T1 200 that's stuck, like you cannot make it 250? That is impossible. Why? Maybe you're writing here, right? That could be the reason. Not up here, not the editor. So in the editor, you are making a file that, see, this is going to be saved right now. I'm going to save it in my desktop or the folder where I keep my homework, right? And this would be there for me so that I can reach it later on. But if you are typing over here, then you cannot change those. Does this make sense? Yes, you need to be able to open the editor and write in it. See, it's under editor. And see, those small, tiny things are really big things. You know, the first time I used MATLAB, what was my problem? It will be really funny. So it turned out that in the file name, you cannot use a bar. You have to use underscore in the file name. So like if I do If I call it rather than, where is it? See how I did underscore and then comment? If I make it like a bar, the program wouldn't run. So there are those tiny things that is like a big deal. For example, in Fortran. So when I did my first program I wrote was in Fortran. It turned out that K, L, M, and N by default are integer, are not real. So they cannot hold digits. And that's the big deal if all the variable is normalized, they go from 0 to 1. So basically everything you calculate is 0. And I stayed like this for like maybe 2 weeks, why my program not running, before I realized that the variable name that I used by default were it. So almost like small things, you can easily get them if you just talk to someone who actually used the program. Question.
Do you have like a general guide that we can use to learn how to use MATLAB or any kind of like starter? Yeah, I mean, I looked online. I actually used it all last semester, and I still know very little about MATLAB. And I try to use the online guides, and they speak in MATLAB language.
Right. So I have a program, a book, but I don't want you. It's called a prime, and MATLAB prime, but prime MATLAB : a prime. But I don't want you to pay more money for books. And second, in the first homework, I gave you the code. So did you manage to just type the code and run it? Yes or no?
I did. I also.
And you had the file, right? So that was the whole idea behind the first homework, was just that you know how to keep a file, a MATLAB file that you can run. A really good source for files to see how they were written is to go to the MATLAB webpage itself, or like they call it Software Exchange Center, and you find a lot of like really cool programs that people wrote that are relevant to students, things that are used in different courses, control and dynamics and solid mechanics, and you just look at them, and I mean, I will slowly ask you to do things and I will explain it to you. So that is the plan. So we will learn how to make a loop, and then we will make how to make a graph. I mean, we will slowly get there. Okay, but for the purpose of this course, don't panic too much. All I need from you, not an expert programmer, but an expert user. Someone who can write like few things, right? But I strongly recommend that you learn MATLAB, not because MATLAB is better than Python, but it's just because any programming language is really cool to have, and they all are the same, more or less. It's just like different syntax, right? And you want to populate your resume with a lot of lines. So by the time you graduate from OSU, I wish everyone would say expert in MATLAB, Python, and C++. And hopefully Julia later on too, if you want to learn Julia. Right, yes.
So another thing about publish.
Yeah, I didn't even explain publish yet. Right. Yes. What's your name? Robert is right. When you go to this publish thing, I was going to explain this. You have to go over here, right? And edit publishing option, and then here, see output file HTML, which is okay, but you want it to be PDF so that you can send it to people, right? So once you do this, and then we publish, he will run the code. And what I really love, beside the fact that like he run and he give you the output, is that part. You see how this is like black, like so strong font, and this is so strong? Why did he do this? Because see those double percentage, it means that this is one section, this is second section. And even when you click.
I'm sorry, can you show the online what you're trying to show us?
Yes, I'm really sorry. I didn't flip my screen. Sorry, guys. So I was saying the thing that you guys missed, that before, this is the menu of MATLAB, right? So that publish menu, over here, you have to say edit publishing option. And under the output file for the default is actually HTML, which will give you an HTML file. But what you want is, you want it to be in PDF. Now he will be able to, you can just hit publish, and when you publish, he will run the code line by line and give you the output. It will look like something like this. See, so that he ran those guys, and then he said, well, then T1 is this, and T1 is this, and V1 is this. And then the solution, and he ran this part, and then he give you H1 and H2 and those guys. So what I also like is like how this is like bold, and this is bold. And I was saying that the reason why he did this is that he thinks that those are two sections of the problem. Why? Because we put this double percentage thing. So that is nice if we have like different part of the code, like maybe different design, and you want to distinguish them in the publishing thing. Okay. One annoying thing, however, is like why he keep repeating all those guys for me. I already wrote, those are given. Maybe I don't want him to reduce the output to the screen too. So the way to do this is to come over here and put this semicolon thing. So the meaning of this is that run it in secret, kind of. I mean, don't share it with me on the screen, right? So even here in the output menu, maybe you don't want to see all those guys. I just want to see the final answer, because I'm going to run it so many times, and just, you know, just keep it for yourself. Just give me the last part. So when we do this, and we just want the X2 and the T2, right? And now we say publish. I mean, we don't have to publish every time. We just could say run. Now look at how neat it is. Here is the code, and here is the two things that we care about. X2 and H and T2. Okay? So I personally like MATLAB because the plotting and the calculation is done on the same software, and he does a great job plotting as well. All right. Okay. Question about the homework or publishing in MATLAB? Okay. Yes.
That's the first law on paper.
So your code started at H2 basically equal to 2,500, H1, sorry, yeah, H2, 2,500, and you just run the X team to get T2 and X2, right? Yes, so is Bibin gonna take points off? No, Bibin is not gonna take points off for this. Is that the right way to do the problem? Partly, half part, like part of it in paper and part in MATLAB? No, it's not. Ideally, in the future, you should make everything in MATLAB. I mean, so here is the problem. Here's what's given, here's what's required, here are the equations. Rather than doing stuff on paper and then just use MATLAB for the last X team. But I mean, because it's the first homework, I think he will be too easy. Don't worry about it. Okay? But ideally, we want to put everything in the code. Yes. So will Bibin take points off? If you don't, no, he will not. Will I strongly, just like masks, you know, the university strongly recommend it. Even today, they send the email saying expected. Masks are expected. Is it required? No, it's not required. Are they dying right now because you are not putting your mask? Yes, they are, but they cannot require it. So because the governors make it illegal to require. But they really expect you to wear it. So I'm expecting you to use MATLAB. Are you required to use MATLAB in the homework? No, you're not. But I'm expecting you to use it. But Bibin take points off you, you come talk to me and give you your full points. Okay, but again, I'm telling you, you have to go through the cell, right? There is like a small mountain. If we just step over it, you will realize how useful it is to solve things in MATLAB rather than in paper. Think about all the trees that you are killing this semester by writing in paper, right? Think about when we are doing MATLAB, I think one of the most educational and useful thing when I was a student that I used to do is to do all those sanity check on my calculation. Like I will take my code to extreme just to make sure, does it make sense or not? Right? So I'm calculating the efficiency. And I know from what the professor said that the efficiency increase with TH and decrease with as we take TH down. So I will done the problem with the temperature he said, but then I will just go and say, what if I double it, the temperature, and then look at the efficiency? On paper, that would be really hard. Who have the time to actually go to the steam table and solve the problem again for temperature that the professor didn't ask for? But when you have it in the MATLAB code, you can just come here and say, let me see, what if it's 1,200? What will happen? And you run, right? And so when you do this, and you run and you look at the number, you will learn a lot and you will make safe about the homework that you just submitted. So things move in the right direction. Okay. In the project, however, you will be crazy. Again, I'm not going to require you. Actually, I did require you. When we see the project, I said write a MATLAB code. So yes, in the project you have to, but not in the home. I was going to say you will be crazy to run it on paper because you are supposed to optimize the design. So that means that you have to run it at so many times. Right? Good? We are good. So I want to start with this. So this is the TAS diagram, right? The real one, not the cartoon that I always plot. This is how it looks for water, basically, right? And so when we have steam that's high, so this is temperature in degrees C. So say 500 degrees C, right? And you send it to a turbine, isentropically, it should go down like this, right? But in real life, it will go a little bit to the right. It will come over here. And that's where you get the work. You start from very high temperature and pressure, and you expand in the turbine all the way down, you get the work. Now, to keep this is just expansion one turbine, but to make this a cycle, what is a cycle? I need to go up again. How are you going to go up again? I cannot just, let's take and heat this guy up, because that would like compress it up, all this pressure. That will take even more work than what you got from the turbine. Okay, what am I saying? I am saying that on this TS diagram, if I have this hot steam like this and I expand, this is 1, this is 2S, actual 2 would be something like this. So now to go to that same place, so I can repeat, I'm getting more and more power. If I come up with a machine that can take this and take me all the way up, the opposite of the turbine, a compressor, right? Ideally, I will go up like this, but in real, to that pressure, right? But in real life, I will actually go like this. Why I'm going to the right? If this is 3, this is 3S, this is 3. Why I'm always going to the right? Why? Help. Why 1 went to the right and 2 went to the right? We're always going to the right. Because the irreversibility, because the second law. So this is actually more than this. The work that the compressor will take you to that pressure is more than the turbine work that you get from going to from that pressure to this pressure. Okay, let's say this is 1.13 megapascal, just like the homework, and this is what, 0.6? No, this was 0.6 megapascal. So to do a cycle, then we cannot just go again up. What do people do? They condense the water vapor all the way to become saturated liquids. Okay? In a condenser, you turn it into liquid. Why? Because water can be pumped so efficiently, so cheaply. The energy of the pump that will take you from the same pressure to that pressure is very tiny. Okay, it's only this much, and that's an exaggeration. Why? Because as you saw in the real TS diagram, this line and this line, they are on top of each other. So I mean, the pump will just like push you up a little bit, and you are there already, because liquid is almost incompressible. Practically speaking, incompressible. Theoretically, no, it's a little bit compressible, but I mean, it takes a lot of energy to compress it, meaning it will take less work to take the pressure up. Meaning the moment you squeeze one more molecule in the place, the pressure go up. Okay, so now once you are here and you reduce the entropy, then you come over here with heat, not work. So that is the Rankine cycle. You are turning that heat into work. And the price you pay beside this is that you have to reject this so that you can go to this point and start the cycle again. So we add Q added, but we have to reject Q rejected so that we can continue the cycle. Right? So in the TS diagram, this Rankine cycle almost look like, right? Except for, what is that called again? What does that cycle look like? What is called? Carnot cycle, right? It looked like it, except that this part and this part, right? I mean, this part is okay, right? I mean, this is not okay, but I mean, they try to make the turbine as isentropic as they can. But in real life, it's not. And that's why in real life, Rankine cycle is not Carnot cycle, because the turbine is not isentropic, right? And the heat addition is not at constant temperature. But see, like you guys thought that it's impossible to do heat addition at constant temperature. It turned out that it's almost possible. How is that possible? Because that heat addition is doing what? Turning saturated liquid to saturated vapor. So when you have phase change, you boil while you are having the same temperature, right? The steam is not gonna get hotter without first all the water next to him go full steam first. Then they can all get hot together. Okay. So what is bad is this part, and you will see today how they try to get rid of that part. I mean, still need to be heated. And I mean, I'm taking you from down there. Carnot said that you have to do this. So if only this can get heated somewhere away from me, if only someone else can heat that for me, then my boiler will just run on the green guy, right? This is not okay, but guess what? If I come here and go down like this so that I can look like Carnot, what's the problem with ending here rather than ending here? What is the difference between this point and this point? No, it is work. I mean, there is work. H minus H. It's the X, X2 and X2. So which one is more wet? This guy. This guy is so wet. So what does it mean? It means that at the end of the turbine, the steam coming at the end of the turbine will have a lot of at the end of the turbine, when the turbine finishes its job, the last row of plates will have a lot of droplets, right? If you end up here, this is dry, maybe one droplet or two droplets. The velocity inside this turbine is so fast. And if you have droplets on them, and they are moving at very high velocity, they will be like bullets. So a turbine running that wet will not last that long. One time we went to Jinx power plant and we were, no, it was not Jinx. Was it Jinx or the downtown one? Anyway, I forgot. I think it was the downtown one. Not downtown, it's just across the river from the gathering place. And they had, the turbine was open for maintenance. And the guy told me and my students, go ahead and touch the turbine plates. I mean, it's very rare to see the turbine open. And we touched the turbine plates, the large one at the end, and it's the saddest thing you could ever see as an engineer. What was so sad? It's pitted. I mean, you put your hand like, oh my God, you feel the agony of that turbine being hammered, shot at, all its life basically being shot at with like small droplets at very high velocity. So you wanna make the turbine dry, and that's why you need to go up, then expand like this, so that you don't end up with very wet steam. Okay, so we saw the cycle on the TS diagram, but how does it look like in real life? It will look like this. Okay, so one of my friends, she actually worked for BSO, and there is this power plant like this, and this is the one in really south of Tulsa. And her sister was not an engineer. And one winter day, when it's cold, that cloud becomes so big, it's as if it does not really go, like it leave here and it basically stay on top of the plant. And her sister took a picture with her cell phone and sent it to her and told her, look what your company is doing to our environment. And of course, we were together in the American Society of Mechanical Engineer section. And she was saying, look what my sister is telling me. And we were all laughing at her sister because her sister did not realize that this is not smoke. This is water vapor coming from the cooling tower. I'm going to show it to you next. This is just H2O, right? Where is the smoke is coming from? It's coming from this. Those are the chimney, the boiler, the exhaust of the furnace, right? And usually those are so clean, right? When I was undergrad, I had my first internship was at a steam power plant. It was like 1200 megawatt. And every day, like the bus would take us a little bit far away, and me and my friend, we would walk until we go into the power plant. I didn't have a car at that time. And we would, every day in that walk, we will bet together which unit is running and which one is not. That's how it was so hard to tell whether it's running or not, because the chimney is so clean. Like the exhaust coming out, just like you watch your car. You actually see the stuff coming from your car. You don't, unless you're running a diesel engine in the traffic light, and the guy stable on the gas and you see the black cloud coming. That's the only time you see. But usually the exhaust is pretty clean, right? So that cooling tower, those are the cooling tower, okay? And those cooling tower will look like this. What's the idea? There is hot water coming from the condenser, right? The condenser that we use to do what on the TS diagram? To turn the saturated vapor to saturated liquid. Someone need to take the Q rejected. Someone need to reduce our entropy so that we can go back again to the start of the cycle. So who do the cooling for us? Water go into the heat, not this guy. Water go into the heat exchanger that's sitting under the turbine and get hot, and then that water need to be cooled somewhere else and come back. Cold and ready for another round. So there's a cooling water cycle, and it get cooled by doing this. So it come here and they spray it, and it go into those packing material. It used to be wood, but then it will rot, and then they get fined by the EPA because they have like rotten wood that go back to and arsenic and stuff. But now they just use plastic packing, so material that does not deteriorate. They trickle it, and the water is trickling like a small waterfall, and cold air is being pulled by fan, and that air, when you go through that water shower, he basically makes some of the water evaporate, with the result of cooling that water. Because the latent heat of the evaporation, someone pay for that joules to turn liquid to vapor, right? So as a result, the water become cold, ready for going back again to the condenser, but the air carries some of the water with them. And the Q dot rejected that the power plant is requiring you to take become M dot HFG. So you can calculate how much steam is coming by just saying Q dot rejected. If this power plant is 1 megawatt, no, it's not 1 megawatt, it's 1 gigawatt. If I have 1 gigawatt power plant and I have 40% efficiency, how much is Q rejected? 0.6 gigawatt. So 0.6 gigawatt need to be rejected in that condenser. I mean, some go in the chimney, but really all the heat is rejected in here. So 0.6 gigawatt is going to be M dot multiplied by HFG. So that is a lot of water. But not all cooling towers are open like this. Some cooling towers are just closed. What's closed? The water never gets sprayed. The water just go into a radiator, kind of, just like your car. I mean, every time your car coolant go into radiator, you don't spray coolant in the air, right? You just keep him in the pipe and it's air cool. So some of them are closed. So that sounds like really good, because I don't want to lose water, but why not all cooling towers are closed then? Why do they still do open cooling tower and lose water vapor to the environment? Because it's not faster, it is. So the fast, it has to do with area. It's more efficient. It can cool you to a lower temperature. And we have a chapter about this. So there is something called the dry bulb temperature and the wet bulb temperature. Okay. So the wet bulb temperature is what you get when you let the sweat evaporate from you. You get cooler than if you just don't have sweat. Imagine if you don't have sweat, it would be really hot, right? But if you have sweat layer that take you down, so that's the same thing for that cooling tower. If it's closed, everything in pipe, you get cool to the air temperature. What's the air temperature outside? 40. That's your dream. Can it get cooler than 40? But if you let water evaporate, it will drop to 30. How is that possible? Because the air is dry and you can take water from you, and that allows you to go less than the dry temperature. You go to the wet bulb temperature. Okay. And then here is, if you look to the main, where is this power is coming from? It's the turbine. See that steam is coming in, and here is the turbine, right? And you go in the middle, because this is actually not one turbine, it's two sitting against each other. Why would they do this? Why do they have it back to back? So imagine if there's only one direction, the steam will come and he's rotating, spinning it, and also pushing on it. It will generate a lot of axial thrust, and the bearing will be under huge, not only they are rotating very fast, but they also will be pushed. So when you put it back to back, you cancel the axial thrust from the bearing. Okay, And actually, they don't only have this guy. This is the big one, but there's two smaller one that you don't see over here. And those two smaller ones are really very powerful. It's actually the high pressure and the intermediate pressure. So what I'm saying is, when we expand in a turbine and we go like this is not done in one turbine. It's done in 3 turbines. Okay, you go like this in the first one, and then sometimes you do reheat, and then you go like this in the second one, and then you continue in the third one. And these two intermediate guys, the high pressure and the intermediate pressure, we put them back to back. So again, they cancel the axial thrust. And then the low pressure one. And all those guys are sitting on one shaft. And that shaft finish with what's on the other side? High pressure turbine, intermediate pressure turbine, low pressure turbine, and what do you think? The generator, the load, the thing that all those guys are driving the shaft to rotate, right? It's the electric generator that actually generates the electricity. Okay. So the steam that get fed to those guys are generated inside the big boiler, right? And again, they call it steam generator, not boiler, because if you go like this, we can see the water is boiling here, going from vapor to liquid. Sorry, going from liquid to vapor, right? This point is called, anyone, what's the point on top of the TS diagram? Critical point. And if the pressure is not 6 bar, but if you go above what? You can see over here, right? So 10 megapascal, 20, right? So if you go above 22 megapascal and you are going from here to here, what happened? You don't go through the dome. You don't turn from liquid and you start making bubbles and then you become vapor. You go through this gray region and you turn from liquid to vapor without bubble. How is that possible? Because at such high pressure, the liquid and vapor have almost the same density. The reason why you see this is that this is very heavy liquid, 1,000 or something, or 900, and this is very light vapor. Different property. But on top of this, it's called basically supercritical power plant. So the first part of your project is to investigate how high we should get. So imagine a regular steam power plant going like this, and then I'm asking you, so if it run at, like what pressure should I run at? Find out what's best. What's the best pressure? So you want to run the calculation for what if it's 10 bar? What's 22? What's if 30? What if it's 40? As you take the pressure up, I want you to keep calculating the efficiency. And then put them in a nice table and say, wow, here is the maximum efficiency. And that can be achieved at that pressure. Okay. So supercritical pressure steam generator are efficient. You will see the efficiency getting higher. What's bad about them then? Why? And the one in Jinx is supercritical. And that's why they don't like you to call their boiler a boiler. They call it you cannot tell them it's a boiler. Yeah, steam generator. We call it steam generator. It generates steam, but not by boiling. Right? Steam generator. So when you go to like this, then it becomes very efficient, and they are really happy with it, right? And and of course it's expensive. Why expensive? Material need to be able to take that pressure, right? Very expensive alloys so that those pipes can take all that high pressure, right? And if you go even higher, that even become more expensive power plant. And they don't call it super quick. They call it ultra quick. Like really, that's the top of the line, basically. The latest in metallurgy technology, right? And so I was gonna, I said that the part of the Rankine cycle that we don't like is that heating that happen. We wish the heating only happened at the top. So the way to heat this part, the way to heat this part is by using feed water heater. Feed water, that's the water feeding the boiler, the steam generator. And so they heat that water by using a bunch of heat exchangers. So this is the feed water heater. You can see it's bunch of pipes where the water will come cold, a little bit cold, and leave hot. Who's heating it? Steam. Steam come here and condense on the pipes, because for him, those pipes are cold. The water in them is cold. So he condenses on those pipes, right? And become liquid that leaves, but in the process, he heat that. You can see how the heat exchanger look like a big pressure vessel. See how thick the wall is? Why? Because the pressure here is as high as the steam generator pressure. I mean, that is the water going to the steam generator. So you basically need to build something that can take the 22 megapascal or even higher if you're supercritical, right? And so this is the actual cycle, right? So what do we see? This is the steam coming from the boiler. So the boiler or the steam generator is actually here in that place. We didn't draw it in that sketch. And this is the steam coming from it, okay? And you can see the pressure is 2,400 PSI gauge and the temperature is 1,000 Fahrenheit, okay? And so this is the mass flow rate. There's a key here that tell you that the mass flow rate is in pound per hour, pound mass per hour. Somewhere. Or maybe in the project statement, I already told you. We are not designing this one. I'm just showing you what's an ideal one would look like, what's an actual cycle would look like. So it comes very hot, right? With that flow rate. What's that flow rate? 3 million pounds. 3 million pounds per hour, pound mass per hour. And it go into the high pressure turbine. And you can see it's on the same shaft as the intermediate pressure, which is in the same shaft as the low pressure turbine. Okay, and you got two of them. And finally, the generator at the end, that's 512 megawatts. And so after they finish the steam expanding, he go into the condenser. And before he go, of course, there is a pump, but then the real pump is actually here. See, that is called PFP, boiler feed pump. So the boiler feed pump is the boiler. That's the one that take you from low pressure to let's go supercritical. That's the one that take you from the condenser, more or less. I mean, when you look at that pump over here, it's a joke. It's like a really tiny pump. Okay, but the real pump is here. And this one will take you to really, that's why those feed water heater that take that high pressure water and heat it, those are like really big things, very, very strong steel, so that they can take the pressure. And it go back again to the boiler to get heated. Okay, so that is the cycle. Now, why do they have a lot of feed water heater, not just one? In your project, you only have one. But in real life, they have a lot because and we will finish with this and we'll take our break. Because what? Because the second law, he told you that the reversibility is coming from friction, but it's also coming from heat transfer across a temperature difference. Why this is a source of reversibility? Because you cannot flip it without work. Heat can seep, can leak from high temperature to low temperature free of charge. Be our guest. You have a piece of ice, come here. You'll give it all the Joule volts, and the ice will melt. But now try to make that ice or that water become ice again. By how? You need to send to a fridge, which run a compressor. So anytime you have something very hot heating something very cold and across big delta T, that is harmful, right? So that's why when I want to heat that water, I cannot use very hot steam to heat that water. I have to heat with, if you look at the temperature coming, you will see that there is only like very small difference in temperature. So every time you heat the water, you heat with steam that is very similar, just to take you up a little bit. And then you take another steam that's very similar and heat up a little bit, and so on and so forth, until finally you are ready to go to the steam generator and become steam so that you can go to the thermal. So 49, so let's take a 15 minutes break and start again at 6:05. 15 minutes. Hi. No, stay here.
I'm making the Zoom link. You say now it wasn't working.
The Zoom link was not working.
Yeah.
Guys online, how did you get the Zoom link?
I don't know why.
Mine wouldn't work. Can you hear me?
Yes, I can.
Okay, so mine wouldn't work, but I had to go through Zoom and act like I didn't make an account through Zoom and I was a guest. So then I just put in the Zoom name and the Zoom password.
So you are saying you have to log in to Zoom in order to be able to watch it? You wouldn't let anyone watch it without an account?
Correct.
Okay. You have an account in Zoom?
I don't know.
You have to make an account free, right? You just have to create an account for yourself.
This only like previous we use it over here. We just click the link and then connect it.
So I know that if you have the meeting ID and the meeting password, that all it takes for someone who's registered.
Yeah.
So maybe you just have to make an account for yourself. Is that too hard to make?
I don't know. I haven't tried it.
Yet make an account over Zoom. Just go to zoom.us and say sign up. I think all they need is your email. So maybe he just wants you to be registered user.
Okay, let me try it.
Okay.
I had sent you a message privately. Could you go check it out, please?
In the chat.
Yes.
Okay, let me read. Yeah, but I actually have to disconnect them so that they don't see it in the class again. Okay. All right, so you said you sent me an email, so I need to check my email. Right, so I'm gonna discuss the project shortly, and then we can see the amount of work that's needed. It's not gonna be that much, so don't get scared yet. This is not the kind of project that require people to work on. And I also think that at the beginning, when you are still guys struggling to use MATLAB, I think if we have a team right now, some of those students will say, okay, you do the MATLAB part, I'm gonna do the whatever part. And so we will end up with people not trying to use MATLAB, trying to get away from it. And so, I mean, I wish everyone get comfortable with it very soon because it's really important. So because of this, I'm not gonna let you get away from it in the first project. Maybe at the end, when you already know how to use it, but you don't like it, that's okay. You can get away from it or find someone else to help with. But at the beginning, I want you to really conquer your fear and use it, right? And if you are worried about the amount of work required, it's not going to be that hard. I promise. I'll spend some time explaining it. Does this answer the question?
Yes, thank you.
All right.
Do you think for the Zoom, the reason why students can't get onto it is because you have it locked after a certain time?
I didn't do that. Let me check my account. I actually don't think I did that. But maybe the IT, because they are the one who set it up. Maybe actually they are the one who did this. You can check the property. It's so small. So I cannot edit now. I'll check it when I go home. I cannot edit because it's already going. But I'll check. So you're saying it says it locks after a few minutes, locks the entry?
Yeah, I know that through other classes, if you didn't log in with the first like 3 minutes, it wouldn't let you log in.
Okay. Maybe they said that somewhere, I didn't see it. But I definitely will unlock it because I want you to be able to log in and log out anytime you want. I mean, if you come late, I don't want you to miss it, especially that we are not allowing people to watch the recording. So it's only fair to allow them to catch it whenever they have a chance to join, for sure.
I was able to log in with the second login actually later.
Okay. So maybe it's just require you to be a registered user to be able to log in so that no one can log in as a guest. Maybe that check mark was there and that's why. That's my explanation. How are you, George? I haven't seen you in a long time.
It has been a long time.
Yes.
I went to work for this bacon manufacturer where I couldn't, just a corporate job I took, I just couldn't get away from it. And I tried a couple times and I just gave up. But with COVID, there were a couple changes in my employment as they drew down. And so now I'm able to come back and finish this up and in the last semester.
Excellent. Excellent. So COVID was not that bad after all, I guess.
Yeah, it seemed like a real negative thing at the time, but then it turned out to be the best thing to happen.
Yeah. Same thing for my graduate student. It actually was a really great year for us because we, like in Tulsa, we don't have that many graduate courses available. Like they have to take the bus or drive to Stillwater to take the graduate courses. You know, we have undergraduate, but the graduate courses, most of them are in Stillwater. But in the COVID year, every single graduate course was available to them. So it was like we were having a blast, sadly. So people were like hurt, but we were really happy that we have graduate courses. So another person is complaining about logging into Zoom. I've been having trouble logging into Zoom for the class today. I will keep troubleshooting. So what is the problem with logging in? Did anyone else have problem logging in? Everyone else is fine except for only 2 students? Okay, so it seemed that the problem logging into Zoom is only if you don't have an account at Zoom. Maybe they don't let unregistered people log in. So if you just have a user account, then that's okay. You only need the meeting ID and the password. All right, so 305, I think should start. So those few slides from chapter 2, let's go through them quickly before we go to chapter 8. Chapter 8 is where the Weber cycle is, the Rankine cycle is in chapter 8. So all this is coming from the thermodynamic book, right? That I listed in the references. So in the end of chapter 2, they are basically saying, what is a power cycle? A power cycle is a cycle where you give it heat in form of hot gases, nuclear reactor, whatever, solar thermal, right? So all the sun is focusing the radiation in one hot spot, whatever the source of heat is. You take that heat and you get it into mechanical power. Shaft rotating. Our job is, as mechanical engineer, is to make that shaft rotate. That shaft take the energy in the form of torque times omega, and you give it to the electric generator. Electric engineering take that shaft, hook it up to a field, and generate electricity out of it. Okay? And refrigeration and heat pump, those are for heat transfer, and we will talk about them next class. Okay, so that is the power cycle, and we said heat, work, some get work, and some leaving as rejected heat. That is the first law. The second law basically insists on this need to exist. This guy, the Q rejected portion, we cannot neglect. That's why it's impossible to have 100% cycle, 100% efficient cycle, because this guy, if we 100% them, all the Q become work. That wouldn't happen, right? And that's the first law that I apply to a cycle that I told you. That simply the Q added is work plus Q out. Okay? And this is the efficiency. So this is what the quiz today is going to be about, by the way. You're going to have a quiz at the end of the class, and it's really remembering this, that the Q added is two parts. Part go to work, part Q to go Q rejected, and that the efficiency is work net, the real thing that we get, and the Q that we pay. Make sense? Okay, and that's when we say you cannot go to 100%. Right? Very cool. So in chapter 8, he starts talking about the Rankine cycle, vapor power system, right? And so sketching the cycle on TS diagram, I think I personally enjoyed it when I was a student. I spent a lot of time coming up with like really neat sketches of the cycle, especially when you have a lot of feed water heater. And I think it's very important for you guys to do this. So that's why in the project, and no, not this one. In the project, I say plot the cycle on the TS diagram. So homework project, full project 1. So project 1, 5% due 9/6. Did I say 9/26? 9/6 at 8:30. So that day we actually don't have a class. So you can enjoy the time studying for the, like doing this. And it's due 8:30 p.m. So it's not due, unlike the homework, it's due 4:30. This one will be due 8:30. So you can have the time to do it. Anyway, so we'll discuss it in detail, but he say plot the cycle on actual TS diagram. By actual TS diagram, what do I mean by this? I mean that I don't want you to draw it like me on a piece of paper. I want you to draw it on this guy. right? And this guy is available in the lecture note and also just available by itself as a file in Canvas. So I want you to come here and actually draw the pressure and go up to the temperature and then go down, right? And so you draw on this one. Say that again. Yes, it make it easy, but also I want this picture to be imprinted in your head. I want you to be able to, when someone, after we do a bunch of this exercise, when someone tell you 1000 degrees C and 32, you know, the bar, I want your eye to be able to remember where was that. You know, I want you to be able to find your places in here. Okay. You say it's easy. I had this in the exam, final exam, I think. Last year, I was so disappointed how many students did it wrong because they didn't really read the right pressure. Okay, so we need to be able to plot it on the TS diagram, and you need to be able to calculate the efficiency for sure. All right, so the simplest Rankine cycle is this: turbine, condenser, pump, boiler. Turbine, condenser, pump, boiler. That's the simplest cartoon. And this is the sketch that I want you to plot too. So when I say plot the cycle on the TS diagram and then make a sketch of the cycle, the sketch of the cycle would be this, if this was your basic cycle. And actually that is the supercritical one, will look like this. Right? Turbine, condenser, pump, and the steam generator. So you want to plot this guy and you want to come on the actual TS diagram, right? And you basically want to mark this like this. Okay. So now in that exercise, he doesn't talk about whether the turbine is isentropic or not. And we will talk about this. But if it was isentropic, that would be 2 and that would be 4S. Right? TS diagram. That is the plotting it on the TS diagram. And the sketch would be this guy. You see the cooling tower, open cooling tower, and the chimney. Of course, this steam generator could be run with a nuclear reactor, right? Doesn't matter what is the source of heat, as long as something is heating the water. And what was funny one time, you know, when they were pressuring North Korea to shut down the nuclear program, and they show like the video that North Korea did comply. And they were showing the cooling tower. They basically put explosive in it and it went down. And they were showing the movie. See, they are complying. They were like, what in the hell? That the cooling tower is not the nuclear reactor. I mean, you could just like be cooling it in the river nearby. As a matter of fact, the power plant that I was interned at when I was undergrad, we didn't have a cooling tower. We just cooling the water in the river. You just send the water to the river and you bring the water from the river. And that's it. And very cheap because again, the pump and that pump running the water from the river to the condenser and back, that's not really that much pressure. This is just a circulating pump. So all you pay for is friction in the pipe, right? The bad thing about using the river for cooling rather than cooling tower is that you bring the water and the fish and the mud. So you stop the fish by having screens, but the mud you don't stop. So that condenser pipe become plugged so quickly. And so every now and then you have to clean it. And you clean it with rubber ball. You shoot rubber ball in the pipes, and there are 3 sizes with 3 colors. One small to clean like really plugged pipe, and then after you clean them, you send the bigger pipe, and then you send the bigger poles, and then you send the bigger ones. And the bigger one, like really squeak clean, you know, when they go, they really clean the pipes. All right. So, and here is a nuclear reactor, right? So you exploding this doesn't mean that this is not working anymore. Right? So you can see how the nuclear reactor, the source is coming from those nuclear rods. They break, fission, you shoot them with neutron, they break into smaller material and energy is released, and that energy is cooled by the coolant. Okay, and that coolant could be just high pressure water that never boil, just go between this and this. Go into that high pressure water so hot that it can make the actual the water that go into the steam cycle boil. But this one does not boil. That's called pressurized water reactor, right? Or you could directly send the water into the reactor. And that boil makes steam and you take it here. And if you do this, that's called boiling water reactor. And that's similar to the one that exploded in Japan, the Fukushima one. Okay. Very good. And again, he's saying, well, you can also do it with solar thermal. So just make the sun heat the cooling, the working fluid over here. That working fluid could be something that has antifreeze so that you wouldn't solidify on in the winter, or could have something that has small nanoparticle. They call them nanofluid. Why would you add nanoparticle in your liquid? To make the conductivity go up, because it looks like as if it's metal. So very high conductivity, absorb the heat very quickly, right? And so, but you wouldn't mix steam. You don't want him to mix steam. You just want him to keep circulating the heat. And then you generate the steam here, right? So your boiler is really a big heat exchanger between the heat source and the water that need to become vapor, right? Or you can take it from underground, like hydrothermal, like in California, and there's a lot of hydrothermal power plant where they take very hot water or very hot brine, because it's a little bit salty from ground, into the boiler, and that generates the steam. Okay. So we want to be able to calculate the efficiency of this cycle. And calculate the efficiency of the cycle, we need to calculate, is it showing the different element? To calculate this efficiency, we want to calculate the work net and the Q added. Okay. And so the work will be calculated from the turbine and the pump, and the Q add will be calculated from this guy. You don't need to calculate that, right? Or if you just want to calculate it, you can subtract this minus those two guys. So how can I calculate the work or the Q added? What do I have? So far, I have only one thing, one tool in my hand, and that is, what is the tool in our hand? What's the name of the equation? Yeah, the first law. We just use the first law of thermodynamics on each one of those four elements. Okay. And so the first law of thermodynamics will read this. It's always like H minus H, H minus H, H minus H. Why is that? Of course, you know, let's go with the steady state directly. Let's forget about the unsteady, because a cycle like this should run on a steady state. So 1, 2, 3, and 4. So when I apply the first law to the boiler, I would say that Q added is, actually, let's write the first law nicely first. Minus W dot equal to let me do this. So I'm gonna say Q dot minus W dot equal to M dot H plus V square over 2 plus GZ minus H plus V square over 2 plus GZ. So when we start the boiler, we will make work equal 0. Why? Because in the boiler, there is no work, right? And also you're gonna cancel GZ and GZ. And we're gonna cancel the kinetic energy. How come? I mean, I saw the boiler, it was like you told me, it was 17 floor high or 14 floor high. It was so tall. So, I mean, obviously the water come at the floor and leave on the top, right? Well, not really, it doesn't really come from the floor because the last feed water heater, the one just go to the boiler is actually in this, like maybe 10th floor or something. But even if that is the case and the water come at the floor and leave from the top, the change in the enthalpy is so much bigger than the change in the kinetic energy and the potential energy. So that's why they always neglect delta kinetic energy and delta potential energy. Will I be more accurate if I consider those guys? Yes. But when you are trying to calculate the wealth of Bill Gates, you really have to calculate it to the cents, how many cents he got. I mean, yes, you'll be more accurate if you figure out how many cents and you count how many shoes he got and how many t-shirts, but like, so how important is it compared to like his actual number? So when it comes to the Q dot edit, yes, calculating the delta kinetic energy and delta potential energy will change the number a notch, but who cares? What the real business is in the H. Bill Gates' wealth is not how many shoes he got and how many t-shirts he got. It's how many stocks he got in Microsoft, right? So forget about the shoes and t-shirts. Forget about the delta kinetic energy. So it just become this Q dot over M dot is H, what? H1 minus H4. The big one minus the small one, right? H1 is way bigger than H4 for sure, right? And that's why this Q will become positive. And that's okay, because we know that the first law say when you add Q, it's plus. So we are fine with Q equal plus number. So the unit of this will be in joule per second. But if you want specific, and let's call it Q added. If you want the specific one, then it's Q dot over M dot. And it becomes H1 minus H4. And that unit would be joule per kilogram. Okay? Which M dot? They're all the same, right? M dot 1 equal M dot 4. Doesn't matter which one. Will that always be the case? For the boiler, yes, but not for other guys. So are you saying that in a turbine, I can come with one flow rate and leave with different flow rate? Yes, you will leave with smaller flow rate. Why? There is a lot of leakage, not bad leakage. It's like we want to take some steam from the turbine to heat something. Or maybe we are using the steam, some of the steam for the glands to keep the air from coming in or something, right? Maybe you are doing it on purpose. But if it's the same M dot, then we don't have a problem, right? And not surprisingly, when you do the turbine, say 1 to 2, and that's the turbine. First law would say Q dot minus W dot, and again, let's not put let's not put kinetic energy and potential energy anymore. So it will be H1 minus H2. What happened to kinetic energy and delta potential energy? They went with the t-shirts of Bill Gates. So it's just enthalpy and Q and W. Now for the turbine may not be isentropic. It may be only adiabatic, but for sure the Q is 0 at the turbine, right? And when you go to actual power plant and you put your hand on the acute blanket, thermal blanket they put under the turbine, you will feel some heat, and then you will question: is it really adiabatic? Why it's so hot? But the fact that you managed to put your hand on 1,000 degrees Fahrenheit turbine and you didn't burn your hand, that tells you that adiabatic assumption is not really that bad. I mean, you put your hand on it. So what, like maybe it's 40 degree, 80 degree, But right, but it's 1,000 inside. So it's okay. It's okay to assume adiabatic. So what I'm saying is that at the end, work turbine will always be just m dot H1 minus H2. This actually should be 2 minus 1. Why? Output minus input. That's the first law. Q minus W is m dot output minus input. Then that minus will flip them. And of course, H1 is bigger than H2, right? This is so big, it's all the way up. And this guy is so small. And that will make work turbine positive. And that's okay for us because we know in the first law, if the work is leaving, it's plus. So we are fine with it. And same thing, you can calculate the specific work turbine, which is m dot turbine over m dot, and become H1 minus H2. Unit is joule per kilogram. Which m dot, it doesn't matter in this case because m dot 1 equal m dot 2. What? You just said that sometimes it's not the same. Yeah, well, if it's not the same, for example, if I'm having a turbine like this, and here is one coming in, but then at a certain pressure, when he reach 2, and before he leave at 3, I took some steam here, m dot 2. This is m dot 1. Then it's very clear to me that what will leave here is m dot 1 minus m dot 2. I mean, I just took this much because I want to heat something. That's what you're going to do in the project. In the project, you're going to take steam from the turbine to heat the water going into the boiler. So in this scenario, if you want to calculate work turbine, because he told me to calculate the thermal efficiency, and I know the thermal efficiency is work net over Q added, I want to calculate work turbine. So what should I do for work turbine now? I cannot say m dot H1 minus H3 anymore. I should do what? Divide it into section and say it's m dot 1 H1 minus H2 plus m dot 1 minus m dot 2. That's what will continue with me, and it's H2 minus H3. Okay, make sense? Yes. And so if you want specific work, this is what a lot of students screw up. So watch out for this part. If you want it per kilogram, you want the joule per kilogram. Then you have to tell yourself per kilogram of what? Of kilogram entering or kilogram leaving? Right? You need to tell yourself clearly it's per unit mass of what exactly. Make sense? So most of the time, you actually want to do it per m dot leaving the boiler. That is the total mass flow rate. That's what we started with. It's going to the steam chest, coming from the steam generator. So maybe you want to say work turbine over m dot 1. Then it will be H1 minus H2 plus 1 minus m dot 2 over m dot 1 H2 minus H3. And the unit here would be of this is joule per kilogram, but which kilogram of steam leaving the boiler going into the turbine, right? And so this ratio is pretty important then. And a lot of homework problem would be calculating that ratio. How much steam are you extracting? Are you extracting 50%, 20%, 10%? How much is needed to do the job that the heating is doing? Okay. Okay, makes sense? So back again to what we are doing. So the Q is m dot H minus H. The turbine is H minus H. The condenser going from 3 to 4. Actually, this was 2. and this is 3, and this is 4, and this is 1. So here is the condenser. Water come from here and go there. Q dot condenser minus W dot equal M dot output minus input. 3 minus 2. You cancel the work because the condenser does not have any work, and Q dot become M dot H3 minus H2. Which one is bigger? 2 is bigger, 3 is small. So this guy will be negative. Q rejected or Q condenser is going to be negative. It's going to be minus 400 or something, kilowatt. And that's okay, right? So, because the first law say that if you reject heat, it should be negative. But here's the confusing part, guys. So if I ask for the magnitude of Q dot rejected, it will be like, say, the 600 megawatt for, like, say, 40% power plant. That's the magnitude. And so when you do the first law and you say that Q dot added, because of the quiz that we're going to do today, Q dot added is work W plus Q dot rejected. This is actually expecting this guy to be positive, right? I mean, don't come in this equation and say, but my the QJ should be negative according to the first law. It's as if when you are saying you are discussing with your family your budget for this month. Let's say I got $1,000 this month. We used say $400 for like really good stuff, food and things, and then you guys wasted $600. You cannot say you wasted minus $600 and then the budget will be 400 minus 600, it will be 200 minus 200, right? In that context, this Q rejected has to be plus because it's the absolute Q rejected. Here is the income coming from the boiler, and we go to two places. Boiler energy is waste or spent in two things: useful work and Q rejected, right? But the point to remember is that Q is in the condenser still m dot H minus H. Now, the last part in the pump. So the pump take you from 3 to 4. And if I do Q dot minus W dot first law, m dot, and I'm going to say output minus input, 4 minus 3. The pump is adiabatic. Go to 0, and so the work pump will be m dot H3 minus H4. Why did I flip the sign? Because of that minus. Which one is bigger? 4 is bigger than 3. So this will be negative. And that's okay for the first law. The work pump should be negative. That work pump is minus 40 kilowatt. Or minus 1 megawatt or 2 megawatt. Okay? It's okay to be negative. That's exactly what the first law said. But when I calculate work net, because why I'm going to calculate work net, that is what is needed for the eta. Eta is work net over Q added. The thing that he keep asking us to calculate in that project is the net efficient, the eta thermal. By the way, this symbol, what is that weird symbol? 1 year, I kept using this, and like maybe after 1 month, the student said, you know, what is that thing that you are doing? It's like, why did you stay 3 weeks before you asked me? What is that? Eta, right? This is my eta. Eta, the Greek letter for efficiency. Eta. So to calculate eta, I need work net. And to calculate work net, what should I do? Work turbine minus work pump. But when I write it like this, then I really need to be correct. I need to do it like this. The magnitude of work pump. If the turbine is giving you, giving you like 400 megawatt and work pump is minus 40 megawatt or something, then in this equation, you actually have to say not minus 40, you have to say minus plus 40. For the same thing, if you want to say what's the work net, you'd say how much did I get minus how much is being subtracted from me. Because the pump, someone need to pay for it. Okay? Make sense? So you will find out that this number, the work pump, is always very small compared to work turbine. Very small. Okay? So if it's comparable, then you did something wrong. Work pump is very small. So how did we calculate work pump? H minus H. How do I calculate this H4? How do I calculate all those H's? So now it seemed that the whole, every part, boiler, turbine, condenser, pump, every one of them, the equation is H minus H, H minus H, right? And if you want to follow the first law, that's what I like to always do. I always say output minus input because I memorized it like this when I was undergrad. I cannot try the first law without saying Q minus W is M dot H output minus H input. And then I write always output minus input, not the bigger one minus smaller one. If you always say the bigger one minus smaller one, you'll always end up with a plus number. So work pump will be plus, Q condenser will be plus. Okay? But if you follow the first law, the Q minus W will always be M dot output minus input, whatever the output is. And then when you do this, you will be happily surprised that, wow, look, the condenser is negative. Then you are okay. And the work pump is negative. Yeah, that makes sense. I buy it because I'm doing output minus input. And the equation is Q minus W equal. But if you do those negative things and you are so happy, I'm so proud that you got the thermodynamics, the first law of thermodynamics correct, and it's negative. Be watch out when it comes to work net, right? And watch out when you are trying to do the first law and you are trying to say Q added is two parts, work net and Q rejected. Very good. Question so far. So you can see here that he is not doing what I was doing, what I was saying. Here he is always gonna do the big minus the small, 1 minus 2, 2 minus 3, 4 minus 3, 1 minus 4. So I think this is confusing. My brain does not work like this. Why it's 4 minus 3 and now 1 minus 4? What's going on? I rather have a recipe and stick to it, which is output minus input. And then when the results come negative, I am like, I know it. Yes, it should be negative. But he in this slide from the book, he's basically saying bigger minus small, right? And then when you say the work pump is like 40 megawatt, he know that you know that the pump consume, not give you power. So when you come to work net, you're gonna do, the subtraction. Right? And so then he do the eta work net over Q, and work net is turbine minus pump, and then he subtract those guys, divide over this. And so those steam or Rankine cycle problem. Rankine cycle problem. You start the problem by basically doing, here's how you solve it. You start with plotting the cycle, labeling it 1, 2, 3, 4, and then immediately you should start getting H1 equal, H2 equal, H3 equal, H4 equal. And you are ready for getting whatever you want. Thermal efficiency, how much steam is needed to generate 500 megawatt in the turbine, but this has to be done immediately. Right? Because chances are you need them. I mean, of course, I'm not saying let's just like get them without reading the problem. No, of course you need the problem and you figure, he needs the efficiency, therefore I need the turbine work and the pump work, therefore I need my H's. As I told you before, we solve the problem from the end, not from the front. We need to put our hand on where is the final answer going to come from, what equation, and then what does this equation require? And then you build yourself up in your head, but then you start the solution like this, because you know that you're going to need them. And each one of those H's will come from knowing two properties, pressure and temperature. So in the project, he said, this is stuck at 1000 degrees Fahrenheit. This is the highest temperature. Okay. So if I just, let's follow the project for a minute here. So a typical gas-fired steam power plant utilizes a superheater, reheater, and multiple feed water heater. As shown, I didn't show. I guess what I wanted to show was was this. I actually had this figure in the project, but I had it there, but I just didn't want you to confuse to think that those are the numbers that you're gonna use. All right. In this design project, you are required to consider an ideal steam power plant. So ideal means isentropic expansion, isentropic compression. So the turbine and the pump both isentropic. Okay, so same entropy. And it's supposed to generate 512 megawatts. Okay, so that is typical. Right? Like the one in Jenks, they have 2 units and each one of them is 450 megawatt, for example. So 512 is typical number. Maximum temperature allowed in the cycle is 1000 Fahrenheit. Condenser temperature, 25 degrees C. The plant consists of a steam generator, a turbine, condenser, and a pump. Please design, we'll talk about this in a minute. But the point is, this is stuck at 1000 and this is stuck at 25 degrees C. Okay. And in the first part, he said, now figure out which pressure you should run at. I mean, you could run at this pressure and you go like this, right? Or you can even run at this pressure and finish. I mean, of course, at one point, you still need to leave at thousands. Right? 1000 degrees C is, so let's imagine that the 1000 will end up being here. That's not a good solution. You cannot leave the boiler at 1000 and with that pressure and then go what? Like, just like spray water in the turbine? No, you need to be on this side. You need to send steam. So this is in red and this is in red. You got this fixed and this is fixed. And it's the pressure that we don't really know which one is optimal. So how are you gonna find out the best pressure? You will try, and every time you will calculate H1, right? And you let the MATLAB file find out, like calculate the pressure as function, calculate like have a table like this, theta, I guess P1 is the design variable and theta is the output. And so you would say, well, I tried this and I tried this and I tried this and tried this, and here is the efficiency. And then you will see where it will be. All right? So again, if we are doing it in MATLAB, it would be just running the code with different P1 every time. And you get, it's super easy. And again, how do we solve the problem, or how does MATLAB solve the problem? This, you start with H's and then you write all those formulas. All those formula after, like the formula for the work pump, it's this one. The formula for the Q rejected is this, right? Every one of them, you can, so after you calculate those H's, then you have Q rejected, Q added, work turbine, work pump. And you calculate every one of them, M dot and type H minus H, M dot H minus H, M dot H minus H, M dot H minus H, and then eventually eta. I mean, you can call it eta or something. Eta equal, and you say work turbine minus work pump divided by Q added. Right? So he actually also asked for the how much M dot is needed to do the job. Look at this. He said calculate the semi efficiency, we just did, and also the flow rate, the steam mass flow rate leaving the steam generator. How can I do that? So I calculate the efficiency from calculating work turbine and Q added. But he's telling me how to calculate this M dot. How? Well, and notice that this turbine is supposed to generate 412 megawatts. So how do I calculate the M dot? The question is there a certain efficiency we are going for when we are trying for different value? No, we are trying to optimize it. So you are trying to find out what is the maximum efficiency you can reach for those test conditions. You are trying to find out how high you can get and what pressure allow you to be able to do this. So how do I calculate M dot, guys, going in from the steam generator? He's asking about M dot 1. Help. Use the turbine equation. That 512, which is work turbine, is M dot 1 H1 minus H2. And we just got H1 and H2, and he said 512. That's how you can calculate M dot 1. Right? You'll do this all the way in all the other combinations. So that is the first case. What is the other case? He wanna us to try different configuration. We'll see why they are doing it. So by the way, there is something also called the the work ratio. What's that? Work pump over work turbine. That number would be, what do you think? Would be almost work pump over work turbine will be almost zero. I mean, work pump is very small, not zero, but I mean, it's really going to be small because the pump work compared to the turbine work is very small. So when you take, if you take 4263 next semester, your heart will be broken when you see in the energy conversion course, like when we do the calculation for a big power plant, we write work pump 0. Like we don't even, the guy in the book that we are using, don't even bother plotting. He doesn't even bother plotting this part of the cycle. You know, like he basically come and finish the cycle here. And sometimes it's actually very important because there's like not just a pump, there is a pump and then there's a cooling tower, and you have to, I keep drawing it for my student in the course because I mean, you need to know the water going to the cooling tower, but the guy does not bother drawing it because or even calculating it, because again, this line, this is very tiny. Work pump is very small. Okay, make sense? Okay, so now I want to say one more thing about work pump before we leave it. So we said work pump is m dot multiplied by H4 minus H3, right? And in each one of those guys require two properties, like the S and the T, or the S and maybe S and B here and S and T over there. I mean, if you know this 25 degrees C and you know that it's saturated liquid, you can get the S. And then you would say that S is the same as that S. Then you come over here, you know the pressure. And you know the entropy is the same because it's ideal pump, same entropy, so you got your H4. But there's also another approximation that is pretty widespread and it's very accurate. It's an approximation, but it's really very accurate. And that is, you remember we said the H last week was what? H is, does anyone remember? H was something plus something. Free quiz, if you remember. You get full credit in the quiz if you remember what was the H. You cannot look it up. You have to remember. You have to really think hard. No, it's not. It is HFG minus HF. No, it's not online, people. No, it is U plus PV. The enthalpy is internal energy plus the flow work. PV is called the flow work. Okay. So work pump, then work pump is m dot multiplied by U4 minus U3 plus B4 V4 minus B3 V3. The internal energy is function of temperature. Do you think when the water go into a pump, it get hot? You think it get hot? Very little. I mean, yes, it get hot. But again, those are the t-shirts and the shoes of Bill Gates. They are nothing compared to the change in insulin. So zero, almost zero. And so then the work pump can be approximated as PV minus PV. And what is that V? Is that velocity? What is that? The specific volume. That's 1 over rho. 1 over the density. That the density of the water change as we pressure it in the pump. Does the density of the water change as I go through a pump? Yes or no? Very little. Yes, it does, but very little. Again, Bill Gates t-shirts and shoes compared to his overall ones. So what are you saying? I'm saying that V4 and V3 are almost the same. Yes, it will change, but hardly. So it's P4 minus P3 multiplied by V3. So people calculate the pump work by simply specific pump work is V3, V4 minus P3. So just knowing the two pressures and the specific volume, or 1 over the density at the inlet, is good enough to calculate the pump work. And this embarrassingly very accurate. I mean, to like few digits, pretty good. Same as let's get the entropy and let's get the pressure and let's read the H and let's subtract from the other H. You get the same thing, just saying P minus P over rho. Why? Because the density does not change that much and the water does not get that hot in a pump. Right? And why all this is true? Because look at the lines. Where are those lines? The 10 and the 100 and the 1 and the 10, they are all on top of each other in that place. I mean, we really have to zoom and zoom and zoom and zoom and zoom until we can, I mean, we don't have enough pixels to show you how those lines are. Yes, they spread over here. Though all those lines spread, those are the pressure line, but they come over here and they all just like one after the other after the other after the other. So you go from none to the other, just one notch and you're there. Right? So we need to be aware that it's very tiny amount. So a practical advice that in the exam, if you're running out of time and you want to get the final answer correct, because there's like 30% of your grade depending on the final answer, you can just neglect work pump and your thermal efficiency or whatever is not going to change that much or little. You have time, go ahead and calculate. And then probably women will take points off for the equation is missing. But when it comes to the final answer, you will not be able to take points off because you have actually the final answer correct, even if you didn't calculate the work pump. So you will end up getting 4, 3, and 4. One equation missing, but the final answer is correct. Okay. All right. So this is pretty close, right? So the ideal Rankine cycle, right? I mean, it's like this, but we cannot do this. We cannot go and hit the turbine with a bunch of droplets. So you have to superheat a little bit. You have to dry the air, sorry, the vapor, make it superheat. And so by the time you come here, you are a little bit drier. So that your turbine, the low pressure turbine, does not get hit with quality that's like 0.8, get 0.9, 0.95, right? So it's a little bit dry. That's the part that I was telling you about. See how the work pump is approximated as V, P minus P, right? So, and that's the part when I'm saying, or like he's saying that the work net is actually what's, the work net is what's under this minus what is Q rejected. Make sense? So we are not asking about this in the project, but if you think about what is the effect of taking the Q condenser down, sorry, the B condenser down, of course it will help. Taking the B condenser down, it will really help. Why? The turbine have H1 minus H2. So the lower H2 gets, the better we are, right? So unfortunately, and they take the condenser pressure down all the way to vacuum, 0.07 bar, 0.03 bar, for example. And so it's under vacuum. And that's why if there's any leak in the condenser, the air will rush in the condenser because he's way lower than the atmosphere. And it does not cost us anything except like, let's just build a good condenser, right? So all that vacuum, the pump will take me from that vacuum to be boiler very cheaply. The pump is very efficient to pressure. So we can build the vacuum that we want, just good tight condenser and a pump very cheaply take you up. The only problem is there is a limitation to how low you can get. How low you can get. Why you cannot go to like 0.01 bar, for example? What is stopping us from going down more and more? What do you think? Free quiz today. You don't have to answer the quiz. What is limiting the condenser pressure? Why you cannot go lower than what is usually they do? What is stopping them? Huh? I can't hear. What about? Can't hear, raise your voice. What about the atmosphere? You are close. What about the atmosphere that's annoying you, that make you not going down? What are you worried about? If you are worried about the pressure across the condenser, no, I mean, if we can make the turbine take 22 megapascal, I bet we can build condensers thick enough to take the vacuum. It's not the pressure difference, yes. I can't hear. The open water? What do you mean the open water? The water will explode? So again, it's not how tight the condenser is. They can build tight condenser. Don't worry about the pressure. What do you mean? No, it's not that. And I'm not talking about the left. I'm talking about down, up and down. Why can't I take the condenser pressure down? Why there's a line that I cannot go less than that? Because I wish I can go down, 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 so that the turbine will have all that, a long way to go. The water will blow, boil, no. The water is, like practically speaking, incompressible, yes, but practically, like theoretically, it does change its density a little bit, yeah. Why is that a concern? No, it's not that. Here is why. I can't hear. The weight of the water, no. No, it is because of, so here's my TS diagram. And we are saying this is okay, but this is even better. And the lower I can go, I will be, so if it's condensing at 60 degrees, that's okay, but 40 would be even better. And 20 is even more better. But I am limited by this. This, what is that? That is, that is the water coming from the cooling tower. The water coming from the cooling tower cannot take you lower than a certain temperature. If the cooling tower is cooled by air at say 40 degrees C, and when the cooling water coming from the cooling tower going to your condenser, it gets heated. It gets heated to what? Above 40. I mean, it's coming at 40 to us. Then it will go up to, I don't know, depending on how much water is going, but it will increase 45, 50. So this is not going to work. You will probably have to set hotter than that because it's cooling you. So what is really determining the condenser is the temperature of the air outside. So on a hot day, that temperature will go up and push the condenser temperature and pressure up. And in a cold day, that temperature go down and take your condenser temperature and pressure down. Okay. I need to, what are we, why this is long? Make sense? So yes, we want to go, but we are limited by the temperature. And by the way, on the top, we are also limited by something. What is it? That is the temperature of the, how hot the turbine can take. The turbine plates, you are shooting steam, and those turbine plates are moving so fast. I mean, they spend, people designing those turbine plates, which look like an airfoil, like this, but they make, if you look at the design, they will have like holes in them that cool them so that they can take that heat. And they coat them with tungsten carbide material so that it can really take all that heat. I mean, there's like special effort material-wise and cooling-wise so that that plate can support the, but at the end, there's still a temperature mix, right? Very good. So, of course, the boiler pressure, that is what you guys are gonna do for the project. But look at this, see how the, when When you increase the pressure and you are limited by a certain temperature, you will start leaving more and more wet. Okay, more and more wet. From thermal point of view, MATLAB doesn't care. He is using the first law of thermodynamics. He calculating for you H1 and H2. Here is work net. Here is the eta thermal, right? But practically speaking, can we allow this to happen? Can we have the last part of the turbine at quality equal 0.5? Can we? No, we can't. But the problem statement doesn't say that. The problem statement didn't say what is the constraint. What is the constraint on the exit of the turbine? As a matter of fact, in most design projects, especially the capstone, there is a lot of things that are not given by the customer. And that's what makes design project harder than homework problem. Because you have to fill in, and sometimes you don't know what is the number, and you have to find that somewhere else. The customer doesn't know. That problem statement didn't say how wet is it safe to run the turbine at? What is the minimum quality? And so the professors in our department, when they actually came up with a way to evaluate design projects, they said 20% of the grade is about this requirement development. So the project is, there's 5 tasks, and you're gonna receive 5 grades from us on that project, in every project, 5 grades. Each one of them is scale 1 to 4. The first one, problem statement, that's easy. That's basically rewriting what I just asked you to do. And that is 10%. You just say, the problem asked for designing a power plant that has this output, the temperature is limited to this, the temperature of the condenser is limited to this. It's done. That's the problem statement, 10%. Now, the requirement development, the thing that you needed to calculate, but was not given, you have to come up with it. And usually you come up from it from design codes, environmental regulation. Like for example, the one project that I give in energy conversion, design solar, basically grid, or like not solar grid, basically a solar powered house. And so I never told them what's the ceiling, what's the roof area, right? So they have to cap their design that we cannot have more solar panel or more solar collector, water collector, more than the area of the roof. They have to assume the roof. So in number 2, you have to search, and that's what's hard, but I'm not going to help you because that's what they want you to do before you go to capstone. You have to be able to get the information yourself, rather than always going to your professor and say, I don't know, what is it? What should I assume? You will find out what is safe for quality at the exit of the turbine, and you would cap yourself into it, right? So you will say, I'm not gonna run anything less than, like anything that make my quality less than say point whatever. You're gonna find the number. Is it 0.8, 0.9, 0.7? And you say anything that will take me lower than this is just out of my search. Make sense? Right? That's one of the limitation that you have to worry about. Okay, good. So the pump work will increase a little bit, but that's not really an issue. I think the issue is how wet you can get. So you cap yourself over there. But in that range, I think you will see the efficiency increase as you're going up. Right? So the superheat is happening in something called the superheater. course. That's funny. And in the actual boiler, so the boiler is like really a box like this or a big building. Usually the fire will come from the wall like this, and so the middle here would be the fire, and then the boiler will basically be like this. So all this is where the wall is covered with those pipes, and those pipes take the water that's coming in and turn it into steam. So this is the part where you go from here to here, from HF to HG. And then once you have steam out, and they will have something called the steam trap over here that take only the steam out and let all the droplets that didn't boil all the way to go down again in another round. But they take that steam, they will take that steam and they will send it to the superheating, which is like basically a heat exchanger like this that is directly on the fire. You know, when you do the grilling, that's the one that's have the direct heat on top of the flame. And then this go to the steam, the high pressure steam turbine. Okay, so after you superheat from here to here, so this would be say point A, you finish at point B. So A and B. Then you go to the high pressure turbine and you expand a little bit. And now you are gonna be really wet. What do? You reheat. So what's reheating? You take this, send it again to the furnace and go back to the intermediate pressure turbine. So that would be like C and D. So once you expand here to C, you take it again to the furnace and you add D. Okay, and now you are ready for the intermediate pressure turbine. Okay, so when we do this reheat, now the furnace is paying for the heating from here to here and here to here, and also this part. Q added is done in 2 stages, right? Taking you from the water inlet to the exit, and then the other part, the heat part. Okay, and so we actually are supposed to design for this. The question is, in a reheat cycle like that, so here is the regular cycle. Okay, and he's saying, can you make it better by reheating? So you come here at that pressure and you reheat, and then you expand in the turbine. So the question is, what is the optimum pressure for this? Should I wait until I become wet, for example, and go to reheat and come back? Or should I like go immediately? And how immediately? So we are trying to find out what is the optimum beer heat. So how do we do this? How do we do this calculation? So 1, 2, 3, 4, 5, 6, right? Just like any cycle, we start with H1, H2, H3, H4, H5, H6. You get all the H's. Ask yourself, can I calculate all those H's or not? H1, how can I get H1? I know the pressure, I know the temperature. H2, how can I get H2? That's the same as entropic expansion. So I know the entropy, S2, and I know the pressure too. How do you know the pressure too? I said that I was trying to find it. Yes, that's why you're gonna put like You're gonna repeat this calculation at different B2. You will start with B2 maybe in the middle, and then maybe B2 a little bit up, and maybe a little bit up. And for every time you know B2, you treat it as an input, and you calculate the efficiency for it. And then you do another B2. Again, on paper, that sounds like so exhausting, but on MATLAB, it's super easy, especially if you do a loop on it. If you just like loop on B2 so that you don't even have to write it yourself by name, by number. Just tell him, calculate it for me from 1 until 100. He will do all of them for you, right? And then come to 3. What do we know at 3? We know the pressure, and most of the time he will tell you how high the temperature is that you reheat. And chances are, based on that drawing that I just drew, is that the reheater will see the flame. He will also see the flame. So he can get as hot as the superheater, right? And because of this, you will see in that cycle, you'd say like it's 2,000, 2,400 psi gauge, 1,000 and 1,000. What does he mean? What is those two temperature? Help? What do you think? What do you think, guys? Anyone? It is the temperature of the superheater, right? And the reheater. He's saying it's capped at this. So the first time he leave the boiler, and go to the high pressure turbine, he's capped at 1,000, and then when he reheat, he go again to 1,000. Right? So in the project, when he was asking you, well, try to figure out what is the optimum pressure for reheating. He didn't say what is the temperature that you reheat to. Okay? So when I read here, a Rankine cycle was a heat stage, but never said what is a heat stage. So in the requirement development, you're gonna, just like you're gonna cap the exit of the turbine, you could also say, I'm just gonna say that the heat temperature is the same as the superheat. If you can heat to 1,000, then you can also heat to 1,000. See that it was not in the problem statement, and you are gonna assume it yourself. Wouldn't it be easy if I tell you what is the heat temperature? Yes, but then you will be just like in a regular course. But a design problem requires you to use your knowledge. What's the knowledge? You know what the boiler look like from the inside. When you think, well, superheater and heater, they both see the flame. So if this guy can go to 1,000, yes, this guy also can go to 1,000. It's not that hard. We can do it, right? Very good. So it's 7:20. So let's take a 5 minutes restroom break. I'll come back. 5 minutes restroom break. Hi. I don't get it. What's the question?
Is this pressure of flow and pressure in one same?
Yes. Yes, correct. Ideally speaking, yes. In real life, they drop a little bit because there's a long line. And so in that line, there is pressure losses, but ideally they are. The difference between them is not that big. So yes, you can see in the sketch, right? See how in the B1 and B4, they are the same? But again, that's a really good point that in real life, it cannot be. All that pressure drop and in multi-phase flow, we will calculate the pressure drop in the line when you are bubbling, and there is a pressure drop, but it's small compared to the pressure in that boiler. The pressure in this boiler is 22 megapascal. So that pressure drop is the number of shoes that Bill Gates have, and how does it affect his wealth?
Right.
Yes, like if he has more shoes, he can be more wealthy, but by $1,000, but he does billions. So $1,000 is not going to break the bank. Yes, there is a pressure drop, but how much will it really drop a 22 megapascal line? Okay, 0.1 megapascal, right? 1 atmosphere, basically, because that's what 1.1 megapascal is. And so what's 1 atmosphere between friends who has 22 megapascal? Hmm? But good point, good job. All right, so let's start again. So you can see here, here's the either heat cycle. You see how he go from 1 to 2 in the turbine, high pressure turbine, 1 to 2, and then he go back again to reheat from 2 to 3. But he didn't go all the way up. In our project, although the problem didn't say under task 2, you would say, I'm gonna take the reheat all the way to 1000. And by the way, in the project, it's very important that each one of those tasks is answered separately. So you cannot just like put it some in the middle and say, well, I did say that somewhere else. No, you have to say task 1, here is it. And add a line, like add a page, it's gonna be PowerPoint, not PowerPoint, electronically anyway. You can start a new Word page and say task 2. Here it is, here's my requirement. I'm gonna limit the quality. Why? Because I saw in the SME professional code that they say that you cannot expose the turbine to anything lower than this quantity. And I'm going to assume that the reheat temperature is as hot as superheat because both of them can see the flame. It makes sense, right? And in task 3, we're going to try those three different setup to see which one make the efficiency high enough. Okay. So here is the heat. Now, when people answer question about this, I always see that the problem they make is, or the mistake they make is usually when it comes to Q added. So they would say Q added is M.1, H1 minus H6. That's wrong. Q added is M.1, H1 minus H6 plus M.1, H3 minus H2. They always forget that part. Okay, make sense? Very good. And you can see how when it comes to the turbine also, turbine work, it's two parts. There is M dot turbine H1 minus H2 and M dot turbine H3 minus H4. You see that on the TS diagram? You get the work turbine is H1 minus H2 plus H3 minus H4. Make sense? Two parts for the turbine work and two parts for the heating turbine. Two turbine, two heating. Right, this is supercritical pressure, how high you can get. And this is how the Jinx power plant look like. They go up, expand, and then they reheat and expand. And that's why they stay. So the reheating really help because it makes you drier on the side, right? At the end. Say that again. Why do you want to be here? Why don't you want to be here? So the question is, why 0.4 need to be dry? Why cannot 0.4 become like here, for example? Because like I can see the point, you are saying, if you are actually very close to the condenser, that means that you don't have that much Q ejected. And so we think Q ejected is like waste. Why would we even want to have a lot of Q ejected? We want to shrink Q ejected. That would be lovely if the turbine allow us to do. But if you go here rather than here, that turbine, the last rows of the turbine, the part that experience this, are being shot at with droplets. A turbine that's here will live 1 year, and you have to scrap that turbine and get another one. This turbine will live 5 years. This turbine will live forever, right? But have low efficiency. So yes, from thermal, you want to have smaller Q injection, but from fluid mechanics, droplets hitting a plate that's moving very fast is horrible. Can you get 4 to be really superheated? From the turbine point of view, I don't know why not, but you just said this is a lot of waste. We are sending a lot of heat to the environment. Our efficiency, it's like basically you have a lot of cash in you, and rather than using it all the way till here, you're saying that no, let's just use it here. So say that again. Yes, it will be very, very good operation from the fluid mechanics point of view, but we are going back with energy into the condenser and we are dumping it. Yes, yes. So we would go down as far as the turbine allow us to be rough with it. Very good. I like it. Actually, I like your questions a lot because it shows that you are really trying to improve this this cycle. And if you think this cycle is well established and there is nothing to be done, you are wrong. There is always ways to improve those cycles actually. And I mean the clear one is the combined cycle, like the one in WAS. The one in WAS was like 65%, not 40%, compared to the one in Jinx. And that combined cycle principle, all the new power plants are built like the one in WAS. And you will be proud to know that the first idea that this combined cycle came up with was actually for the whole world, was in Partsville. They figured out a way there with the steam and catch fire. This idea basically became the thesis of combined cycle, which is now all the new power plants are built this way. The reason why Jinx 1 is just like this without combined cycle is because it's really old. All right, so now the irreversibility in the system, of course, efficiency of the turbine. So for this project, we assume isentropic, but in real life, it can be a little bit irreversible. And you measure the difference between 2S and 2 by eta turbine. You can see how it's H1 minus H2 divided by H1 over H2S. So it's what? He's saying it's ideal work over actual work. Efficiency is always small over big. That's why it's like 90%, 85%. So who is smaller? The ideal work. So who's smaller? The actual work, H1 minus H2. And who's bigger? The ideal work, 1 minus 2S. And that's why you see eta turbine is H1 minus H2, the actual small, divided over the bigger, H1 minus H2S. Okay? So in the project, the last task that people every year lose points over, like every time in the final project, I hardly find anyone that gets 4 out of 4 in task number 5. And I keep telling them, please pay attention to this task, but they don't. What is this task? So when we read task number 5, which is 20% of the course of the project grade, it's a risk and design compliance verification. So what is the risk calculation? Few or no risk identified. This plan. So basically, your design, you are assuming a lot of things that you think it should be okay and this is going to be safe, but it's not. And so in task number 5, you try to assess those risks to say, are those calculations of this design is really going to work, or like this was just like too childish? It's not going to work like this either. So, for example, the turbine, we are assuming ideal turbine. Okay, we calculated everything assuming isentropic, and the pump is isentropic. That clearly is not true, right? So the question is now, if we actually use real turbine efficiency, isentropic efficiency, and again, you will have to find this yourself from other textbooks, from web pages, and you think, well, actual turbine will have an efficiency of 85%. How does this change my final design? I calculate my final design, and I said it will require this much MDOT, and it will have this efficiency. If I employ those guys, how does this change my number? So why people lose points over this? Because they just talk about it without actually doing the calculation. They just say, I think the turbine is not going to be isentropic, and that's going to be a big mess. But how big is the mess? Is it 5% mess or 90% mess? Is it something that we can live with, or something that if we really have to rebet? So I'm not asking you to calculate every single thing, but like find what is the most horrifying assumption and assess them. And what's really nice is that even if you don't know the number, you cannot find. I mean, that's why you assume isentropic, for example, because you didn't know. You couldn't find the number. what is nice is that you could basically say, here's worst case scenario. The worst case scenario is, I've never heard about anything that's less than 70%. Let me assume 70% and see how much is it. And so even if the worst case scenario results in very small change, then you'd say we are safe. Huh? This would be true in this pump. So we are saying that as isotropic pump, you can easily say, well, let me assume 50% pump efficiency. And that is horrible. Not really that horrible, actually. It's like 50 is okay. So assuming 50% pump, how does this change my eta thermal? And you do the calculate for the whole thing. What is the whole thing mean? You're gonna just change this point. This point will be a little bit up. And how does this change things? Well, it will change work pump a little, and it will change Q edit a little. I do the calculation, get those two guys, calculate eta thermal, show that eta thermal for the whole plant just change 5%, for example. Then I'm saying, okay, that design is okay. Less than 10%, we are fine. We are not designing NASA a mission to Mars. Huh? So if it's like 10% or less, we are saying, well, we will write the number, say that the change is less than 10%. Okay, so in task 5, you have to pick some of your assumptions. I mean, ideally, you wanna pick all the risk assumptions and assess them, whether with real number that you work a little bit harder to get them, or worst case scenario. Okay, make sense? For example, look at this. I mean, this guy, this reheat cycle. What is the relation between P1 and B6? P1 is the pressure leaving the boiler into the turbine. B6 is the pressure of the pump. What do you think? Same, P1 higher, B6 higher. Huh? B6 should be higher, of course, because of the pressure drop, but that TS diagram suggests, looking at that TS diagram and showing this line like this, what is that line? Constant pressure. That line is constant pressure. So he's saying it's ideal. Really, 17 floor boiler with tiny pipes and steam trap and superheater, and all this has no pressure drop. Of course, it has pressure drop, right? But considering that the pressure of this guy is like 15 megapascal, I mean, what is the pressure drop in your pipeline, even if it's that long? So that is, that thing that you can assess. You can basically say, I'm assuming no pressure drop in the pump, and sorry, in the boiler, through the boiler. But I mean, let me just figure out if that's a big deal or not. I mean, basically say, well, assuming that length, that flow rate, I know the pressure calculation. What's the pressure drop in a pipe from fluid 1? F L over D V square over 2G. That's the head loss, right? F, Moody chart, L over D V square over 2G. And you basically say, well, yeah, it's like, 100 kilopascal, but man, I have 20 megapascal. So 20 megapascal minus 100 kilopascal, that's like 19.9. That's okay. Actually, no, it's 19.09. Because one bar is 0.1 megapascal. Right? So anyway, so that's what's needed by task 5. We need quantification, numbers, calculation that basically show what is the value of those assumptions. Are they too much to buy, to swallow, or no, they are okay, they are not that bad. All right? Good. So this is again how we quantify the efficiency of the turbine. So don't use it in the calculation, but if you want to use it in task 5. Because the problem said assume ideal. Then task 5, you will say, well, let me check how this change things. Let me calculate everything again with that efficiency. How does this efficiency change? It will change the position of 2. So rather than 2 here, 2 become here. So the work will be a little bit smaller and the Q rejected will be a little bit bigger. So I mean, you lose on both sides. You get less work and you get more Q rejected. Right? So the Q added is basically losing on both sides. And the same thing for the pump, of course, except the only thing about the pump is because the second law always said go to the right, 4S is here, but 4 is to the right. So now work actual is actually bigger than work idle. So while the turbine efficiency was, the efficiency always small over big. Small over big. So for the turbine, it was, who was on top, who was the numerator? Work actual. And ideal was at the numerator. Here is the opposite. The ideal work is in the numerator, and the actual work, which is bigger, is in the numerator. So it's flipped. 4S minus 3 over 4 minus 3. Make sense? So in those calculations, what happened is that you get 4S first. You get H4S. How do I get H4S? Knowing the pressure, it's the same as the boiler, and knowing the entropy, it's the same as the exit of the condenser. So you can get H4S. And once you have H4S, you come here and say eta pump is 50%. I know 4S and 3. I will use this equation to get 4. So this equation helps you to get the actual insult from the ideal insult. When you get the ideal insult from, it will go up straight. Same for the turbine. We go with isentropic ideally up, and then we use the equation to calculate the action. All right? Questions? Something. All right. So now those two guys, again, as we said, the Carnot cycle is a rectangle on the TS diagram. And what we have is not a rectangle. Horrible. One, 2, 3, and 4. And so this part is not okay. I should have something like this. That's my Carnot cycle. But I mean, we need to heat him here. And so they figure out that I can heat this using what? Using that steam. I can take steam from here, send it over there, right? And use that hot steam, all this. Yes, I will have less m dot going forward here. If this was, if what's coming here was 1 kilogram per second, and you pull m dot here, then over here you have 1 minus m dot kilogram per second. So you have less work, and you think that's bad, but that steam that will take that water from 4 to say like 5, that heating help the turbine, help the boiler to look more like this. Constant temperature heat addition. So that arrangement of making some of the heating happen by steam from the turbine, and although it reduced the work of the turbine, but it really helped amazingly the efficiency. The second law, like you for doing this. Okay. So the question is, how much m dot is needed? So here is how they do it. They come at point 2, while the turbine is going from 1 to 3, it's going to continue like expanding. They come from 2 and they pull the steam Huh? They send to big chamber that mix with, there is a tiny pump here and go from 4 to 5. And that 5 go with 2, and 2 and 5 together make 6. 2 and 5 together become 6. And that 6 now get bumped up to the boiler pressure, and it go at 7. And from 7 till 1, that is heating. That's the Q added. That part, the heating from 5 to 6 is internal. When it comes to the first law, you just look at the big box and you say, I give you Q added and you give me work net. Therefore, your efficiency is work net over Q added. Now, what's happening inside, that's not my concern. Doesn't show up in the eta thermal equation. Okay? So the question is, how much are we pulling? How much need to be used for heating? Wow. Help. What do you think we should do? One. So we go up to that pressure, and then so 1, 2, 3, 4, 5, 6, and 7. And so if this is m dot 1, and this is called m dot 2, this what will come here is m dot 1 minus m dot 2. So the third part of the project is this, and he is wondering what pressure you should do the heat at. What is the optimum? What is the optimum pressure that will make this will increase the efficiency? But I mean, you can imagine if you do it like really close over here, that will not really be great idea. Why? Why pulling from here is not great? Yes, you are losing a lot of work, but also because what else? For a free quiz. Why pulling steam that hot to heat the water is not a great idea? Good job. Free quiz. You don't have to do the quiz today. You get full mark. Because why we are doing this in the first place? Because we didn't want the hot furnace to heat that cold water. That's big reversibility. Well, if I take something as big as this one, what did I do? It's the same thing, right? So you will see that the eta optimum will actually be very close to, what do you think now? Of the temperature, right? It will be very close to a pressure that will put the temperature, a pressure that will put the temperature in the middle. T optimum, more or less, is in between. Okay, and so in those real power plant, when they have 7 feed water heater, what do you think they do, more or less? They take that big delta T and they cut it into parts, more or less. Tuck, 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 and they put the pressure on it. So that every, like the temperature is like increasing with the same delta T in between. Okay. So required is m dot 2. I need m dot 2 because if I don't get m dot 2, how I'm gonna get my work turbine? I mean, at the end of the day, eta thermal is work net. You want to write this because that's your project. Work net over Q added, right? And that work net is going to be m dot 1 h1 minus h2 plus m dot 1 minus m dot 2 multiplied by h2 minus h3, right? Plus, sorry, minus work pump 1 minus work pump 2. And each one of those work pump, is going to be m dot h minus h, right? M dot going into it. So work pump 1 is going to have different transfer rate than work pump 2, right? Divided by Q added. What's Q added? M dot 1 H1 minus H7. Make sense? So the question is, what is M dot 2? Because I need M dot 2 to do this calculation. How do I get it? Work pump 1 and work pump 2. I just didn't have space for them to write. So minus work dot pump 1 minus work dot pump 2. First pump and second pump. So how can I get m dot 2, guys? Look at what m dot 2 is doing. It's coming from here and losing all that heat to the water so that the water can come up like this. So this chamber, it's called open feed water heater, where you have two flows coming in and one flow leaving. You have m dot 2 coming in like this at H2, and you got over here m dot 1 minus m dot 2 coming at H5, and everyone leave with m dot 1 multiplied by H6. And I'm asking you to calculate m dot 2 for me. How do you do it? This is the control volume, right? What happened? What? I don't know what happened to this guy. Are we kicked off in Zoom? Can you guys hear me online?
Yeah, I can still hear you.
Yes.
Yeah, I just lost my tablet. I don't know why, what happened. Though he's connected to the battery and everything. Oh, he was not connected to the battery. Oh, really? Okay. So I was saying you just have to apply the first law of thermodynamics on this. Okay? So when you do that, when you apply the first law of thermodynamics, you will be able to calculate m dot 2 divided by m dot 1. And that's all you need. You just need the ratio. Right? And you see the equation over here. Right? So I don't want you, there is formulas written for it, but I really like you to say m dot times h plus m dot times h equal m dot times h. That's energy in equal energy out. Why I want you to do this? Because in some calculation or some cycle, there are more than 2 guys coming in and 1 guy leaving. Sometimes there are 3 guys coming in and 1 is leaving. And so, yes, this is correct for this particular case with those particular number, huh? But later, maybe you don't want to do this. Make sense? Right? So he calculate, those are all the equations that you need for the project, right? The work turbine, the work pump, the Q, and eventually the, so this is called regenerative cycle. What's a regenerative cycle? It's a cycle with feed water heater. The feed water heater is used to help the pump, to help the boiler. So the boiler does not have to take the water from very cold from the condenser and take it all the way to H1. The boiler does a smaller job. Okay, so now here is, I know that the project now sounds so scary, man, what are we gonna do all this? It's not that scary because in task 3, you are not optimizing any of them. You're gonna just calculate one, like one case of each one of them. So an ideal cycle with supercritical pressure, he just wants to calculate for one pressure, one critical pressure, what is the heat? We are not searching for an optimum. And you want to calculate one cycle with reheat. Which pressure reheat? Just one value. You go ahead and calculate the number for it. So for each one of those three design, so this is called preliminary design. So in the design process, you need to be able to come up with a rough calculation first. Okay. And comparing those three guys, they always say in our department, you have to have at least three. But for us, three is good enough in this course, right? But in capstone, you should have at least three designs. So that means four or something. So you do those three pieces, one example of supercritical, one example of reheat, one example of our feed water heater, regenerative cycle, right? And based on those, I just want you to pick your favorite. Ideally, you will also pick the one that is best. And then you make it even better. How do you make it better? By, in task 4, you make it better by writing that MATLAB. So that's not an option. You have to write a MATLAB code for it. Even if, I mean, I would write MATLAB for those, but you don't have to. Those you can just do it them by hand. And here in task 4, you write a MATLAB code that optimizes this cycle. What do I mean by that? He would run it at different value and report the efficiency, tuck, 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 until he find out, so see under heat, the optimum pressure is the one that does this. Okay. And what's really beautiful about if you did it in MATLAB is that now you can, so you said that the pressure was say 20 megapascal, and then you're trying to find the reheat, and you turn out, well, the reheat was like 15 when this guy was 20. And you're like, what is the relation between them? Is it like 25% or 50%? With MATLAB, you allow you to do the experiment again with different boiler. You say, now let me try for 25. What would be the optimal heat? And then soon you'll be able to come up with like really a chart that will always have the ratio between the heat and the boiler at different boiler. And if that number is almost constant, you come up with your own ceiling, which I know because I read the book. But you will be able to figure out what here is the ideal reheat for whatever pressure. I know now what is ideal pressure. Just like I told you, the ideal regenerative pressure is the one that put the temperature in the middle, right? Good. So we have a lot of time for the project. That's not due yet. And so next time we'll talk about plotting. How does plotting can be done in MATLAB really easily. So we have 2 minutes for the quiz, and I want to show you also the homework that's due next week. So it's a very one problem for your homework. Okay, it's gonna be easy. And the homework is this cycle. This is actually the Jake's power plant. When we visited there, I asked them for their flow chart, and that is their flow chart. Now the boiler is actually sitting over here. Okay, that's where the boiler is. And again, it go to the high pressure and then go back to reheat and come back from the heat, go into the intermediate pressure, and then from the intermediate pressure, go to the low pressure, and then go to the condenser, and then bunch of feed water heater until he leaves. Right? And he's telling you how to read it. What is W and what's the units basically. When, for example, when say that the W is 3 million, what's that? That's the mass flow rate in pound per hour. Pound per hour, that's W. Okay, the H is BTU per hour. So what is required? Calculate the required steam flow rate for the last feed water heater number 7. Okay, where is it? This guy. He's asking you for how much M.7 is needed. How do you do that? The water is heated by that steam condenser. So what do I do? First, law of thermodynamics. Q equal Q. M dot, which is this 3 million times the delta H. Where is the delta H? I have the H here and the H here. M dot times delta H equal to M dot that I want time delta H. Done? Q equal Q. The one that's heating is equal to the one that's cooling. Okay? Got it? Yes? I just love that you actually see an actual power plant rather than the sketch in the book. I want you to see the real one. So that if you end up working as an engineer there or something, you look at this chart and say, yeah, I saw that before. Calculate the total heat added at the boiler. Okay, what in a cycle with reheat, what do we say the Q added is? Q, the original one, H minus H plus Q, what's the part that always students forget? The reheat part. So where is the actual one? This is the water going in. So I got my 3 million multiplied by, this is the H, the 486, and it come back 3 million multiplied by that H. That's the main heating part. And the reheat is this part. From the reheat to the reheat. How much is going? 2 million. 2 million is going to the reheat at 1,200, coming back at 1,500. Piece of cake, right? Q is Q plus Q. What's Q? M dot delta H plus M dot delta H. Got it? Yes? Tell me now if it's not that important, clear. You just add the 2Q. Third part, the hardest part. Please calculate the plant heat rate. What is that? I didn't say that. The heat rate is the opposite of the efficiency. The efficiency is, what's the efficiency? I can't hear. Work over Q. Work net over Q added. The heat rate is Q over work. So when we really love the efficiency to go up, the people working in the power plant, they love the heat rate to go down. Because that is the energy, the natural gas they are burning, divided by the electric energy they are receiving. So to get this, so what I'm saying is that this is 1 over eta. But eta is, what's the unit of eta? What's the unit of eta? The efficiency. What's the unit? Is it meter, kilogram? It's dimensionless because the power is in megawatt and the Q added is in megawatt. But the heat rate, because that's the natural gas, and this is electricity, they turn the joule into BTU for the Q, and they turn the joule into kilowatt hour for the power. What am I saying? I'm saying is that, so 1 over eta is supposed to be Q over W, okay? Q is joule per second, and W is joule per second. What over what? They don't want to keep it joule per second over joule per second. They want to turn the joule on the top to BTU, and they want to turn the joule at the bottom to megawatt hour. Sorry, to kilowatt hour. Why do they do this? Because they sell the kilowatt hour to us at 11 cents, and they buy the BTU from the natural gas company. And so they want to see this number. And when this number is 9,000, they are happy. When this number go, or like 8,000, it's happy. When this number go to 10,000, when they climb up, that means their efficiency go down. So they panic. When this number go to 10,000, like, oh my God, we are not making money here. Because they are paying a lot for little they are making. So what is this heat rate again? It's 1 over eta multiplied by a number. What is this number? You will figure this number by converting the joule to BTU and the joule downstairs to kilowatt hour. Okay? I can give you this number, but I don't want to give you this number. I want you to get into that mood of we have to get the information ourselves. It's challenging. You will hate me for it, but you will thank me when you go your capstone. Because you say, we did this so many times. In every design project in 3, 5, 2, 4, we actually have to come up with the definition ourselves. It's not a big deal. We can get it. Okay? Make sense? All right. So now actually I think you can get the quiz online. Or if not, I guess I can just click on it. So remember 80% of the quiz is telling me, are you attending online, or if you are in class, you have to write your seat number. And you get 80% of the quiz. The other 20 is by answering this. Yes, question.
Let's do it. 8:30.
Yes, correct. Too much, too little.
That means we gotta stay here.
No, you shouldn't, because you can solve this in 5 minutes. I'm gonna leave personally, but if you wanna hang until 8:30, go for it. But this problem, you can answer it in 5 minutes. What
Are
do
we,
you,
using-
go ahead.
are we using roll call attendance this evening?
No, we are not. You're gonna write in your answer sheet, whether you are online or whether you are in class. And if you are in class, you're gonna write your seat number in your answer sheet. And you upload that paper as your quiz, and you upload to the Dropbox. Does this make sense?
Yeah.
I can't hear you. Raise your voice. Okay.
Yeah,
So
it
the
makes sense.
problem said turbine of a gas-fired steam power plant generate this much BTU per pound, and its feed water pump, the pump, basically pump of the plant, consume this much, and the steam generator consume this much energy. That's what Q added. Calculate the thermal efficiency of the plant. You won't eat a plant. He give you work turbine, he give you work pump, and Q added, and he's asking for eta thermal. You can answer this in 2 minutes. Yes, it actually, because you have to write what's given, you're right. You have to write what's given because Pippin is gonna grade this on 3 scales. You have to write what's given and what's required, and then you write the equation, and then you give him the final answer. And so if you don't write what's given and what's required, you're not gonna get the first 4. That is correct. It probably can take 5 minutes. Fortunately, it's 8:06, so you still have fun. What is the symbol for? What is the symbol for the steam generator? What do you mean the symbol? Yes. The steam generator is a boiler. It's Q added. Q added. The question is, what is the symbol for the steam generator? And the answer is Q added.
Dr. Salom, will there be any more discussion? after
No, we
this?
are done. If you upload your quiz, we are done today. Thank you so much. I'll see you next week.
Thank you.
All right. I am leaving. You guys write those three number, okay? So 520 BTU per pound for the turbine, 8.27 BTU per pound for the pump, and 1094 for the steam generator.